Hello.
Good morning.
Good morning.
అదేంది అట్లా బుజ్జి ఇలా 2 నిమిషాలు అయితే 10 అవుతుంది. మేము వెళ్ళిపోతాం అత్తయ్య ఇప్పుడు. ఏమొద్దు. అమ్మ వండింది ఆల్రెడీ. కొద్దిసేపు వెనక్కి పెట్టాలి. కనకాంబరం పూలు ఉన్నాయా? కూర ఉంటే మొన్నట్లా వెళ్తే మొన్నట్లా వెళ్తే తీసుకుపోతా, లేకపోతే మొన్న నెలవా 10 రోజులకి అన్ని వెళ్తాయి. ఎండకాలం చెప్పు. నిన్న మొన్న తీసుకుపోయినా ఈ రోజు అరటిపండ్లు తెచ్చిందాను. 3 అరటిపండ్లు
Is this color okay? Blue?
Yeah.
Yes, sir. Works perfect.
Acha, where is the cordless?
Okay.
Go one that. So are we live?
Keyboard not deleted. Okay.
Hello. Are we on air? Hello, welcome to IITMDS Mathematics and Statistics Academic Cell. And this is the third day of our offline event. And today is the final workshop, and we have our prize distribution also coming up. So we have our very favorite professor Amritamsu Prasad with us from IMSC. And I would like to call Sarang sir on stage, our favorite professor from Foundation, right? to introduce Amritamsu sir to all of you. Thanks.
Yeah, hello again. So it's a pleasure to have Professor Amritanshu Prasad here from the Institute of Mathematical Sciences. Coincidentally, I'm doing this for the second time this week or in the last 2 weeks anyway. So he was here last week as well to give another very nice talk. So maybe today I'll give a little bit of background. So he's from the Institute of Mathematical Sciences. He did his BStat from the Indian Statistical Institute, and then his PhD from the University of Chicago. And after that, he's been in Mat Science, which is next door, since 2003. 2003 on. Okay. Okay. Today he's going to tell us about the quaternions. Thank you.
Okay, so good morning. I hope you can all hear me in the room also. Okay, so I'm going to talk about something called the quaternions. How many of you have heard of quaternions? Oh, okay. So you may have heard the name. Do you know what they are?
X numbers have 3 dimensions. If we had one more dimension,
Yeah. Okay. So it's a number system basically, right? And it's okay. So it's a number system, but it's a funny kind of number system. And so let's try to also understand what are number systems and where quaternions fit in. And then I'll talk a little bit about how it's used in computer graphics. So this the story of quaternions goes back to an Irish mathematician. His name is William Rowan Hamilton. He was born in 1805 in Dublin, where he lived for most of his life. And and you may have heard this name in other contexts. He was also like an accomplished astronomer and a physicist. And in physics, there's the Hamiltonian formalism for solving physical problems, which also works very well in quantum mechanics and so on. It's a different way of, an alternative to Newton's equations for solving physical systems. But this thing that he discovered is a very, very beautiful thing. So you must have seen, so I'm sure you've all seen real numbers, right? So there's this set of real numbers, and they have, we can draw them on a line, for example, right? So we have, we can draw the real numbers 0, 1, 2, 3. But there are also numbers in between the integers, and there are numbers like square root 2, which may not be rational numbers. It's a continuum of numbers. And what we can do with them, we can add them, we can multiply them, we can subtract, and except for 0, we can divide by a real number. So that's a kind of a number system, and you can you can axiomatize it. You can say that okay, the real numbers have these two operations. They call them binary operations, addition and multiplication, and then there are various rules. And we learn these rules quite early in life, maybe in class 2 or 3, and they're so deeply ingrained in us, we don't even really think of them as needing to be made explicit. And then you may have seen complex numbers, right? So complex numbers. So one way to think about complex numbers. So of course we think of a complex number as something like a plus bi, and we have this rule that I squared is -1. Okay, one of the problems with real numbers is that negative numbers don't have a square root, and this is kind of solved by introducing the complex numbers. And we tend to draw these real numbers, these complex numbers on the plane. So let me see if I can not. Okay, so I want to move this down a bit. Yeah, okay, great. So let me introduce another idea that will be useful later on, which is how do I get it back? Oh, yeah, okay, yeah. So which is thinking of numbers as actions. So if I have a real number, say let's call it a, I can think of a as an action. So what is what is the action 2? Action 2 means double everything. Okay, so I will call that f sub a of x means multiply x by a. So real number can be thought of as an action. What is 0? just multiply everything by 0. So everything becomes 0. It's like just contracts to a point. And what is so f of 2 is doubling. What is f of minus 1? Not in additive inverse, right? So yeah, take x to minus x. And when you do actions, you can do them one after the other. So I can first, what is f of half of x? So just x by 2. So we can think of these as actions. And the thing is, you can do one action and then do another. So for example, I can do f of minus 1. And then I can do something like f of 3 by 2. So yeah, so this is minus, sorry, I should say f of minus 3 by 2. So these indices, they get multiplied when we compose actions, when we do them one after the other. So we can capture the multiplication of real numbers by these actions. So we can think of them as acting on the real line itself. This line here, we can think of them as acting on the real line by dilating it, or maybe even taking the things to their negatives and so on. So we have this this I is square root of minus 1. So what does minus 1 do? What minus 1 does is it takes 1 to minus 1, right? It takes 2 to minus 2. So if you wish, you can think of minus 1 as rotation by, well, here it doesn't matter whether say clockwise or counterclockwise, because 180-degree rotation clockwise is the same as 180-degree rotation counterclockwise. So rotation, let's say counterclockwise rotation by 180 degrees. So now I'm looking for an action, I'm looking for an action that would be a square root for minus 1. So something which if I do 2 times, I want to do the same thing 2 times, and I want to end up with 180-degree rotation. So what should I do? Yeah, but geometrically, what does it do? What should I do twice so that, so suppose I'm facing this way, right? And I want to face that way. Yeah, I should just turn by 90 degrees 2 times. So this f of I should be counterclockwise rotation by 90 degrees. And this is why we try to think of I as the number. So if I take, so fa of 1 is a. So where do I mark the number? I mark it, I mark a where fa takes 1. So where does fi take 1? So it's the point, I guess I can call it 0, 1 if I use Cartesian coordinates. So so what I can do is now I can draw this what is called the imaginary axis, and here also I have 1, 2, but this 1 is actually I. Okay, so this is the reason why it's so nice to draw complex numbers in a 2-dimensional plane. It just extends, and this notion that it is a square root of minus 1 becomes then very natural to think. I could have also done clockwise rotation. After all, it's the same thing. So I made a choice here, and all the stuff that we do works perfectly fine if you draw I below the x-axis, but nobody ever does that for some reason. But you can do that also. So that would be, minus I, and that would also be a square root of minus 1, because if you take the negative of something and square it, the minuses cancel and you get back a plus. So we have minus I here, and we have plus or minus I. These are the square roots of minus 1. So we can do this, and then we can think of any point in the plane as also being a number. And so if we take, for example, so if I take this point here, which has x coordinate 2 and y coordinate 3, then I will think of it as 2 plus 3i. So these complex numbers, we have created a new number system here. Always have trouble with this. Okay. So it consists of numbers of the form a plus ib or bi, I don't know sometimes. And the only rule that you need to remember is that I squared equals minus 1. Just using this rule, you'll be able to figure out any multiplication. Addition is just, you add the real parts and the complex parts. Using just this rule, you can figure out how to multiply any two complex numbers, but you still need to remember the rules that you learned in class 1 or class 2 in school, that is addition, distributivity, and things like that, right? So we can do that. So we can compute a plus ib into c plus id, and we get ac, and then we get, so we'll just use distributivity to expand this product, and so we'll get ac plus iad plus ibc plus I squared bd, but I squared is minus 1. So we'll use this rule here that we have, and using this rule, we will have minus bd. And so this I can write as ac minus bd plus I times AD plus BC, which is again completely of this form, right? It has some real thing plus I times some other real thing. So this is another complex number. So we have a, so we have has addition, has multiplication, and these addition and multiplication, they satisfy various rules like a plus b equals b plus a, that is called commutativity. There's a plus b plus c equals a plus b plus c, which is called associativity. And then we have, like, there's a zero, there exists a special, there's something special called zero, which if I add to anything, that's a. And then there's also the axiom that every number has a negative. So in the real numbers, if you go to the right by some amount of zero, the negative is the number to the left. So a plus minus a. And multiplication has exactly the same kinds of properties, with the only slight difference that 1 times a is equal to a. And what we have is a into a inverse equals 0. A inverse only exists if a is not equal to 0. 0 does not have an inverse.
A into A inverse is 1.
Oh, sorry. Yeah. Good point. Yeah. Yeah. So yeah, a into a inverse is 1. And that can only work if a inverse is not 0, because you multiply anything by 0, you have to get 0. So these, you can think of this as a system of axioms from which all properties of, well, not all properties, but all the algebraic properties of complex numbers or real numbers can be derived. So far, these are common to real numbers and complex numbers, right? These are also common to rational numbers, and I don't know if you've seen clock arithmetic, modular arithmetic. So there's this, axiomatic method in mathematics where you first fix certain rules which everybody agrees upon, and often you take those rules to be something that is evident. So Euclid, maybe more than 2000 years ago, started this, where he gave certain rules for geometry, and so these would be considered the rules for arithmetic. And they're common to complex numbers and real numbers, but complex numbers has this additional property that -1 has a square root, right? What's so special about -1? Well, okay, it's a nice number which didn't have a square root earlier, but there are lots of other numbers which didn't have square root, like any negative number. Now, any negative number will have a square root. But in fact, there's a very powerful property which makes complex numbers very special, which is called the fundamental theorem of algebra. So saying that -1 has a square root is like saying that the equation x squared plus 1 equals 0 has a solution. Because if you take this equation, you can write it as x squared equals -1. The solution is a square root of -1. So you can think of it this way. Now, there are many equations over the real numbers which don't have solutions. You've seen this while solving quadratic equations. Actually, the only equations which don't have solutions over the real numbers are certain quadratic equations when the discriminant is negative, b squared minus 4ac. But this kind of uh, once you sort of to algebraize, this kind of behavior is very annoying sometimes. We want to be able to, you have a matrix, you want to always be able to find an eigenvalue. If you And these kinds of issues keep coming up, and somehow it's better to work in a system that is closed. So when we study numbers, we first study positive numbers, right? 1, 2, 3, 4. And then when children are small, they ask, what is 3 minus 5? And then that's like some mind-boggling concept, right? And then later we say, okay, we'll just close it. We'll throw in all the minuses which you didn't have in first standard, we'll throw them in second standard or whatever. And then, so then you have like, but then what is 3 divided by 2, right? So that's some other mind-boggling concept. And then you throw in rational numbers. And now we have like, what's square root of -1? And then we throw in these complex numbers which you can't even they don't measure things in our real world. Our world is somehow real, but still, okay, at least we can visualize them in the complex plane, right? What happened? This thing is all right, so we can visualize them in 2 dimensions. But the thing is, somehow this, not just to negative numbers have square root, there's the fundamental theorem of algebra. So it has such a grand name, it must be very important. And what it says is that any polynomial, except, okay, so if you take non-constant polynomial. If you take the polynomial 1 is a polynomial, it's a constant polynomial, it doesn't have a solution. Any non-constant polynomial has a complex solution. So if we want to solve equations, complex numbers are enough, right? We can solve all possible, well, at least polynomial equations, we can solve them all just using complex numbers. And that's a very nice thing about complex numbers. But Hamilton was looking at this from a purely another slightly different viewpoint. You can think of complex numbers as a rule for multiplying pairs of numbers. So I can take this thing here, what I worked out, and I can write it as a rule for multiplying pairs. So I have AB into CD is equal to AC minus BD, comma AD plus BC. So I take 2 pairs and I talk about some mysterious operation which multiplies them, and I get another pair. But the important thing is that when I do that, I have all these axioms holding. Okay, in that sense, it's quite remarkable that, okay, so for real numbers, these axioms they seem very natural. We first saw them when we talk about counting numbers, natural numbers, and so on. But even for real numbers, this seems very natural, but it's quite amazing that for pairs of numbers, we have this kind of multiplication rule. And Hamilton was obsessed with this. So he wanted to know, can I do this for triplets? So can I have some multiplication rule like A, B, C into, ABC into maybe D, E, F, and then maybe some really complicated or maybe not so complicated formula. And then I want these operations. I want this thing to happen. How do I copy this? Well, you know what I'm talking about, right? So I want all these things to happen. So I want the addition. Oh yeah, there's one more thing. No, how are addition and multiplication related? Right, that also we learned in school. A into B plus C is AB plus AC. So Hamilton was obsessed with this question. Can I know how to add them. Okay, so let's not mess with addition. We can add just component wise, we can add them, and that will have all these properties that addition is supposed to have, like commutativity. If you just add vectors component wise, it will have this property that A plus B is B plus A plus associativity, 0, everything will work fine. But you have to define multiplication so that it has all these additional properties. And I think the year was 1843, and Hamilton was obsessed with this. And in October, he writes like how his 9-year-old son every morning would ask him, "Papa, have you been able to multiply triplets?" And Hamilton would say, "No, son, I have only been able to add and subtract them." Right? So, but then on 16th October, he was walking. So this is like a very, I don't know, maybe somebody else would have discovered them, but still, this is like how it happened. On 16th October, he was walking with his wife alongside the Royal Canal in Dublin, and suddenly, like, he was hit by this idea, right? It wasn't, unfortunately, a rule for multiplying triples. It was a rule for multiplying quaternions, quadruples, fours of numbers. Okay, and he carved on a rock, he scratched out on a rock the following equations. 1843. He carved on a rock the following equations: I squared equals J squared equals K squared equals IJK equals -1. So this is the analog of saying I squared equals -1. So now you have three kinds of complex i's. Okay, so each of them square is -1, but their product is also -1. So okay, so he carved this. We look at what this means more later. And there's still, I think there's a plaque. I haven't been there, but there's a plaque on Broom Bridge across the Royal Canal with these equations now written on it. So it's like a pilgrimage for algebraists to go to Dublin and look at the plaque on Broom Bridge. Very simple looking equations, and in fact, this allows you to multiply quaternions. So firstly, let me say what is a quaternion. And so quaternion Q is of something of the form Q0 plus. So now there's an I, Q1 plus J, Q2 plus K, Q3. And sometimes we put, arrows on top of these I, J's and K's. Being a somewhat lazy person, I might skip that. But in books, they might show them also in bold letters. So, so this is a quaternion, and just using these rules, we can figure out how to multiply quaternions. It's not clear entirely, so let me just So how do I multiply, for example, so these were these Q0, Q1, Q2, Q3 are real numbers. Okay, we often write three-dimensional vectors in this form, right? I, J, K coordinates, like with the right-hand thumb rule. I, J, K. This finger's I, this finger's J, and this finger's K. With I being the x-axis, J being the y-axis, and K being the z-axis. So we can think of this as a vector in three-dimensional, the space where we live. So sometimes I'll use this notation Q0 plus Q, the vector Q, which means this is a vector in three-dimensional space, which is usually denoted R3. So, so these are real numbers, and this is just some real number. Okay, I've been rattling along, but maybe I should have paused a little earlier to ask if there are any questions about things so far.
Hello, sir.
Yeah.
Shubham this side.
Yeah.
Sir, just a confirmation, maybe I have missed, you have to repeat again. Like this Q, which you have written Q is equal to Q naught plus I Q1. So this Q is called quaternions, na?
This is a quaternion, yeah.
A quaternion. Okay, got it.
Yeah. Like
Thank you.
A plus IB is a complex number. This is a quaternion. Collectively, all these things will be called the algebra of
Quaternion.
quaternions.
Okay, got it, sir. Thank you.
And I need to still convince you. Yeah. So any other questions? Okay. So yeah.
Exploring how is it related, as you said, it's related to the multiplication of the quadruplets.
No. So it's not at all clear. All that is. So this is what he wrote, and so let's explore that a little more carefully. How do we multiply? I didn't tell you like how to multiply anything. I just wrote down some rules, but from these rules you can actually do everything. So firstly, let's see. Special examples of quaternions. You take Q0 equal to 1, and you take Q1, Q2, Q3. No. So it's not at all clear. All that is. So this is what he wrote, and so let's explore that a little more carefully. How do we multiply? I didn't tell you like how to multiply anything. I just wrote down some rules, but from these rules you can actually do everything. So firstly, let's see. Special examples of quaternions. You take Q0 equal to 1. Okay. So shall I continue, or it's recording? Okay. So yeah, so you can take Q0 equal to 1 and the others to be 0, and then you just get a real number. You could take Q0 equal to, you could just take Q1 equal to 1 and Q0, Q2 and Q3 to be 0, and you'll get another number which you can think of as a kind of imaginary number. After all, it's I, right? So you get a square root of -1. But if you take, again, you take Q2 equals 1 and the others to be 0, then you get something called J, and that is also a square root of -1. So there's like 3 square roots of -1. So the imaginary part of a quaternion, we can call this the imaginary part. So I'll call this the real part, and I'll call this the imaginary part. Okay, so this imaginary part has 3 components. It's a 3-dimensional. So in the complex numbers, the imaginary part was just 1-dimensional. Now the imaginary part is 3 dimensions. And so I have like these special quaternions called I, J, K, and 1. 1 is also a quaternion. Okay, so clear. So let's see how do I multiply I times J. So I want to understand how to multiply I times J. I look at what Hamilton wrote, and I don't see any rule clearly for multiplying I and J, but maybe I can combine these rules to get I and J. So let me try this again. I should not be. So if I think this should be No, what did I do? Oh no, that's how do I copy? Ah, yeah, edit. Should be an easier way to do this. Ah, okay, now let's introduce some. Yeah, get it. Huh.
Here I is complex number or the
Yeah, so what is I right now? I don't know, because you can think of it as a complex number, but then only one and I, right? A plus IB, then that will be complex numbers.
is it I vector axis or axis?
This I is different from that I. So yeah, you can think of it as a vector axis, but it's also part of a quaternion. So if you look at the imaginary part, it's just part of the quaternion. So let me go to the next page. I'll just rewrite this. So the rules that Hamilton wrote were I squared equals J squared plus K squared plus I J K. This is equal to -1. And let's see, how do I figure out how to multiply I and J? This doesn't tell me, right? So any ideas? What should be the product of I and J? K, but why? So let's look at this. Ijk is -1. And let's multiply it by k. Okay, ijk is -1. So this is okay, so this is so I can do it in two ways. This into this, so that way it is minus k. And if I do it like this, k squared is -1. So this is minus ij. Yeah, so minus minus cancel, so ij is equal to k. So what we get is ij is equal to k. Hmm? No, that's afterwards. But if I'm just saying, if you only have these rules, yeah. So afterwards, of course, it is like I into j is k, and I think you may have seen these rules. J into k is I, and k into I is j. So it's like I j k. This into this is this. This into this is this, and this into this is this. So you can derive all these rules just from these Hamilton's equations. Yeah. For example, you can also do. So now I know that ij is equal to k. So let me multiply this on the let's multiply this on the right by j. So what do I get? Ijj equals kj. But now j squared is -1, so I get kj is minus I. Okay, so you can play with just these rules, and you can get all the rules for quaternions, namely ij is k, ji is minus k, jk is I, kj is minus I, ki, ij, ki is j, ik is minus j. All these 6 rules you can derive from these equations here. So, and this will allow us to multiply any two quaternions. So let's just do one multiplication for the sake of yeah. Okay, so let me do some special multiplication. So suppose I have a vector u in 3-dimensional space. So I'll write it as ix plus jy plus kz. So that's a vector, and I have another vector v, which I'll write it as and let's call them r and s. R and s, and let's call this uvw. I have two vectors, And I can think of these as quaternions with the real part, that is that Q0 will be 0. So can think of them as quaternions. They're just so-called imaginary quaternions. Remember what I was meant by imaginary? Just this part, no real part. So I'm thinking of these, and let's just multiply them. So it's slightly simpler than multiplying general quaternions because there's no real part. So this is like multiplying two imaginary numbers. You always end up getting a negative number, right? So let's see what happens here when I do this. So let's multiply these. So we'll use those rules which I had in the previous, here. Okay, I hope you remember them. They're not. So let's just multiply RS, and we'll use the usual rules of arithmetic that we learned in school. But you know, there's one rule that seems to be broken here. Which rule is broken here? So let's look at all the rules here. Which of these rules is broken?
AB equal to BA.
Yes, AB equals BA is gone, right? AB is minus BA for I and J, and God knows what happens for general quaternions, right? So yeah, so that is gone. So this is gone in quaternions, and that's
AB equal to BA.
yes, AB equals BA is gone. There it goes again. Okay, minus BA for I and J, and God knows what happens for general quaternions. Yeah. Okay. So yeah, somebody's probably listening on 2. Okay. So let's do this. So we don't have that rule, but I hopefully everything else will work fine. So we have to multiply. So oops, let's not use the red. So Ix plus Jy plus Kz, and let's multiply. Iu plus Jv plus Kw. And so can you tell me, so I just take one term from here and one term from here, multiply them and add up. So if I take Ix times Iu, what do I get? Minus Xu. Okay, let's try to get the real part first. So also if I take Jy and Jv, then I get minus Yv, and then I get minus Zw. And that will be, I think, the only real part, because if you take I or J and you multiply different ones, then you'll get different. So that's the real part. Okay. So then how do I get I? So I first I can take J into K or K into J. So if I take J into K, then I'll get YW. And if I take K into J, I'll get minus I. So I get minus ZV. You guys okay with this? I'm using the rules from up here, these rules, right? These rules. Okay, and then J, what is it? Let's see. So how do I get J? I have to look at Ki and Ik. So Ki, so K into IZU minus Ik is XW plus K times, and so Ij or Ji, so XV minus YU. Does this ring a bell? Does this look familiar? Let me just change this a bit. That is true. What about this real part, XU plus YV plus ZW? And what about this thing? This is the dot product, right? So this is minus dot product of RS. And what about this thing? What is that? What's the other thing? Cross product. Yeah, this you look at this is exactly cross. Remember this cross product I, J, K, X, Y, Z, U, V, W. I don't know. I was taught to remember it as this determinant. And that's exactly what you get. YW minus ZV, right? So
Cross product.
cross product. Yeah. Okay. Yeah. So uh, so it's actually very nice when you just multiply imaginary quaternions. Unlike complex numbers, now you also get an imaginary part. This is the imaginary part, and this is the real part. The dot product is the real part. You get the negative of the dot product. So you get a negative number as the real part, which is the same as in complex numbers. But you also have this cross product here. So somehow, this Hamilton's struggle with multiplying um quadruples or whatever triplets is what he was trying. It seems to have revealed something which somehow captures a lot of geometrical ideas that we use in whatever vector analysis. So both dot product and cross product just pop out of this quaternion multiplication. Let me just tell you what the axiomatics behind this is. So it's actually the quaternion product satisfies all these axioms. There's an addition, there's a multiplication. Addition is commutative, multiplication isn't. Okay, they are both associative. There's an additive unit, which is 0. There's a multiplicative unit, which is 1. Every quaternion has a negative, and every non-zero quaternion has an inverse. So these axioms, so the earlier axioms are called axioms for a field. These axioms are called axioms for, so with AB equals BC, it's called a field, and without AB equals BC, it's called a division algebra. So it's just a name, so division algebra. Algebra just means, rules for addition and multiplication. Division algebra refers to the fact that you can divide by anything that's non-zero. And then you may ask, the story is somewhat disappointing because what about triplets, right? Is it there or is it not there? Here we have a product, we multiplied triplets actually, but what is wrong with this? Well,
We
the
have a
product
real part here. We have a real part which creates the problem.
This is closed under multiplication. The product is no longer a triplet, right? It has this real part. So we couldn't actually multiply triplets. So
Sir, I
this
have one doubt.
Hmm.
Sir, I wanted to ask that how did Hamilton come to define the quaternions the way he did? So how did he derive that interpretation as he did?
Yeah, I don't know, but he was thinking about it for a long time and probably trying out various things. There's one nice way to express these things, but again, it doesn't answer your question, I think. I'll just come to that in a moment. There's another way of thinking about these things in terms of matrix algebra, but I really don't know the answer to your question. How did he come upon this? It's
Plus
one of
also,
those
sir,
things. Hmm.
Also, sir, we have seen this in graph theory and group theory. So we have seen that quaternions form a group under multiplication in that way. So we can form graphs of those groups using the Frucht's theorem and all that. So we have seen a lot of symmetry over there this way. But sir, here I'm not able to see that sort of symmetry and those
Yeah, you'll see it in
interpretations.
a bit. Yeah. So quaternion groups, which you're talking about, they were actually, I think, historically they came up later, right? And group theory itself as a subject came into its own later. So uh,
Okay.
this notion of abstract algebraic structures was still in its infancy. Uh, and what I'm talking to you about now is in fact about axioms and so on. That's sort of abstract algebraic structures. If you take advanced algebra courses, there'll be algebraic structures, and they'll give you like these endless lists of axioms to memorize and so on. So this is like one of those. The division algebra has all these properties. Yeah, so I don't know how. It's a great question. Is there some like recipe? Many things we can kind of like imaginary numbers, it's not so difficult to come up with it. And I tried to give you some geometric idea of, how we should visualize them and so on. It's not, yeah, here it's, I don't know of any such very clear thing. And triplets, how do we multiply triplets? So in 1877, Frobenius, who's also one of the founders of representation theory, which studies groups, he proved that there are no other. So if we are looking for number systems which contain the real numbers, which have all those axioms, then the only possible ones are the only number systems, the only division algebras, let's say. Now I've defined division algebras containing R, containing real numbers, are, well, real numbers themselves, complex numbers, and I should give this a name, Hamilton quaternions. So this is the usual name for it, Hamilton's quaternions. And the proof actually is, the proof is nicely explained even in the Wikipedia article on quaternions, Frobenius's theorem, I think, if you look at it. It's not very difficult. So if you're, if you know a little bit of algebra and so on, you can go look for the proof. So there are only 3 possible such systems. So what Frobenius has proved, the impossibility of multiplying triplets or 5 tuples or 6 tuples to get a division algebra. There are other ways of multiplying 4 tuples, for example, 2 by 2 matrices. They can be multiplied, but that's not a division algebra. Why not? So which of these? That is removed anyway for division algebra. So which of these axioms is not satisfied by 2 by 2 matrices? And there's a rule for multiplying 2 by 2 matrices, right? And there's a rule for adding them. And it's clear that if you add, it's commutative, it's associative, there's a zero. So which of these rules fails for matrices?
AB is equal to BA?
That's out.
So the inverse always doesn't exist. So we can't always. So like.
True, actually.
For if it is 0, means like the determinant is 0, then we'll have some problem.
Inverse doesn't always. That's right. So you take, for example, this matrix, right? 1, 0, 0, 0. That's out. Non-zero matrix. And please mute. Yeah. That's a non-zero matrix, and its inverse doesn't exist.
True, actually. For if it is 0, means like the determinant is 0, then we have some problem.
Inverse doesn't always. That's right. So you take, for example, this matrix, right? 1, 0, 0. Could you please mute your mic if you're not speaking? Yeah. Okay. So this axiom, this because of this matrix, 2 by 2 matrices don't form a division algebra. So so Frobenius's theorem doesn't talk about those. You can have 3 by 3 matrices which form a 9-dimensional algebra, but it doesn't have this division. Not that every non-zero thing is. So in that sense, these quaternions are very special. So let me show you how to divide quaternions. It's a bit like dividing complex numbers. So how do you divide complex numbers? So you have a plus ib. The key to understanding division of complex numbers is to do this calculation. A plus ib into a minus ib is a squared plus b squared. And so I can write it as a plus ib into a minus ib divided by a squared plus b squared is 1. And so long as a squared plus b squared is non-zero, I can divide by a plus ib. So a plus ib inverse is the complex number a over a squared plus b squared. plus I times B over A squared plus B squared, provided AB is not equal to 0, 0, right? So every non-zero complex number can be divided. This thing is called, if this is Z, then this is called Z bar. Similar thing works with quaternions. So if you have Q0 plus, let's use this vector notation. So this is the imaginary part. So this is IQ1 plus JQ2 plus KQ3. And you multiply it by Q0 minus Q bar. So let's do this. So this gives us Q0 squared. And then, okay, let's first figure out the real part. So the real part will have two contributions. One is multiplying the real parts. If you multiply this Q0 by this vector part, you'll just get Q0Q. So that will go to the vector part. So the only other vector part calculation you'll have is Q into Q. So that will be the minus of the dot product. So you'll get, but then there's a minus sign there. So you'll get plus Q dot Q, which is the same as the norm of Q squared. Right, and then you ask what is the imaginary part. The imaginary part, well, there's Q0 times my Q with a minus sign, and then there's Q0 times Q with a plus sign, and then there's the cross product bit, Q cross minus Q, but that's 0. And all this is just 0. So all this cancels out. So all you're left with is this real number. What is this? This is just Q0 squared plus Q1 squared plus Q2 squared plus Q3 squared. Because this is just Q1 squared plus Q2 squared plus Q3 squared. So this we call the norm of the quaternion itself. So this is the quaternion norm. And now you know how to divide quaternions, right? You just take this and divide it by its norm. That will be the inverse. So that's quaternion division. And this shows that quaternions actually form a division algebra. Every non-zero quaternion has an inverse, because non-zero means that norm of Q is is positive. So yeah, so they form a division algebra. Yes, I told you that matrices don't form a division algebra, right? But still, you can find the quaternions inside 2 by 2 matrices. I'll write them down. So one is just the identity matrix. 2 by 2 complex matrices. I is the matrix I0, 0, I. Please pardon me, I'm overusing the symbol I. This is now the complex numbers wala I, the I of complex numbers. J is 0, 1, minus 1, 0. K is 0, I, 0. If you wish, you can sit down and check that Hamilton's rules, I squared equals J squared equals K squared equals IJK equals minus 1. Minus 1 means minus identity, are satisfied by these matrices. So in fact, once I write it like this, you know that matrices satisfy all the other rules except for this, division rule. All the other rules, associativity, blah, blah, blah. So then you can see that quaternions actually satisfy all the other rules of multiplication by checking that these matrices do so. You can also realize complex numbers inside 2 by 2 matrices. Just take inside 2 by 2 real, these are 2 by 2 complex matrices, right? Do you know how to realize complex numbers inside 2 by 2 real matrices? So you can take, you just need to find a real matrix whose square is minus 1. And that's actually, you can take one of these matrices. Maybe this is a real matrix, right? So you can take this and this. This will give you complex numbers inside 2 by 2 real matrices. Take this to be I, this J. So in the same way, you can get quaternions inside 2 by 2 matrices. This, I don't think this is how, I don't know if Hamilton thought of this, but here's a sort of, when I suddenly pulled out these symbols I, J, K, and then I said, we'll write down, I mean, that's what Hamilton did anyway. And then he just wrote down these rules. It's not clear, where they came from and how to think of them, but it's somewhat more reassuring if we can write them as matrices. Okay, so matrices, 2 by 2 matrices, that too with complex entries. But still, it's something that would have been familiar to people at the time of Hamilton also. But the other very nice properties that quaternions have, and they've been used, for example, in astronomy. I wanted to spend some time on this, but maybe I'll just state the thing. And they're used a lot in computer graphics to compute rotations. So when you're making a video game, either you're, from the POV, you're turning around, or objects themselves in the game are being turned, and you need to implement these rotations. And so you need to compute this rotation matrix, and every time I sit down to compute this rotation matrix, I get all confused and the coordinates get mixed up and so on. There's a really nice formula using quaternions. So I'll just write down the formula and I'll tell you what it is. And you can, I mean, again, nowadays you can look up everything on Wikipedia and work it out. Yeah, I should write down. You can write down the proof somewhat slick way using this vector part and so on. So rotation, quaternion rotation. So the formula is basically this. So I'll think of action RQV. So Q is a quaternion, V is a vector, and I will just define this to be Q, V, Q inverse, where this V will be an imaginary quaternion, IJK. And what is this? I claim that this is a rotation. So what is this a rotation about? So let's take Q to be Q0 plus Q. And let's say R is the norm of Q. Then I can write this as R times. Then this Q0 will be less than or equal to 1, right? So I'll call that cos 2 theta. So just solve that equation. What is the angle theta for which it is cos 2 theta? Sorry, sounds a bit weird, but this is how it works out, okay? And then this thing is, this has norm less than or equal to 1, because this thing plus q squared, this thing's norm squared plus q squared is 1. So let's say the square of this norm is sine 2 theta times 1. So let's say Q0 by R is cos 2 theta, and let's say norm of Q by R is sine 2 theta. Then I can write this as sine 2 theta times U, where U is a unit vector. Then this is a rotation about the axis. So every rotation has an axis and an angle, right? The Earth's axis, and then there's an angle. In 1 hour, it rotates like 1/24 of 360 degrees. So about the axis U and angle theta. Just using quaternion multiplication. It's so simple. It's actually very fast to implement also on a computer. You just implement IJK, the rules for multiplication, and you can just compute this very fast without any head spinning. You can build this. You can take R equals 1. R somehow doesn't play any role in this. It's a rotation about the axis U and angle theta, so there's no R. So just create this quaternion cos 2 theta plus sine 2 theta times the unit vector, which is your axis. Right, so you have an axis which you know presumably when you're programming the game. what you're rotating, or usually you're rotating x-axis, y-axis, or z-axis, but often things are tilted and then you want to rotate about some arbitrary axis. So the axis is just given by a unit vector, two diametrically opposite points on the sphere. They define an axis. So you just take one of them, that's your axis, and then there's a right hand rotation rule. If you take this one, then the angle is the other way around. So you get this, and you can try to play with this and see if it actually works. For example, take the axis to be the x-axis, like the I, and see what happens, whatever angle you take. So you must have seen that complex numbers can be used to implement rotation in the plane. So quaternion is slightly more complicated, but of course, three-dimensional rotations are also very complicated. And later on, much later when I was in grad school, I learned that the group, there's this, you can think of all the rotations themselves as forming some sort of a space, like like our three-dimensional space or a sphere. It forms a space, and that space is actually what is called the real projective space. It's r cubed. It's S3. So these Qs, these can be taken to be unit quaternions. Each quaternion gives rise to a rotation. So you get a map from unit quaternions. Each unit quaternion gives rise to a rotation, but two opposite unit quaternions give rise to the same rotation. So there's a 2-to-1 map from unit quaternions to rotations. And this is something which seemed somewhat mysterious to me when I was in grad school, and then my teacher didn't tell me about this very nice construction using quaternions. I don't know why. So maybe later, you'll find these things interesting if you study geometry. But I should stop. I think time's up. So. Hello. Can take some questions. Yeah, I think she's. Hello. Hi. I don't know. Okay.
Hello. 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 Yeah. Thank you, everyone. So, and thank you, Amritanshu sir, for the talk. We are opening the floor for question right now. Any more questions from audience? Yeah, sure.
So, like these quaternions can be used in place of rotation by matrices to rotate. How how does it help in improving the time complexity of that algorithm in whatever way we rotate?
So, okay, so I don't know if the time complexity improvement is so much, but the simplicity is one thing. But the other thing is you see that right away that you're just using 4 coordinates to express a rotation. Whereas if you were using matrices, you would be using 9, right?
So operations will
Yeah, so it will reduce slightly, but I'm not sure it's such a big savings in terms of time complexity.
it's constraints.
Yeah. Uh,
How to rotate it about any particular axis, for example, IJ or K, what to do?
Yeah, so I'll let me do one example. So suppose I want to rotate about the I-axis, then I must prepare this at an angle theta. I-axis, which means x-axis, and angle theta. Let's say angle pi by 4, right? So then I should prepare this cos 2 theta, sine 2 theta, right? So cos, yeah. So I hope I didn't do the ulta. Okay, yeah. So Q will be so cos 2 theta, which is 0 plus 1. So just I. So what I get is that right? So I get so R
it will be on y-axis. Because 90 degree rotation.
Yeah, so let's just work this out. So RQ of V is IVI. So what happens to the different axes? Maybe I got it wrong. I should take theta by 2, is it? So IVI. So suppose I take I itself. No, see, now what is happening? If I take I, then I get I, which is minus I. If I take J, I get IJI, which is KI, which is J. And K goes to K. So I think, so this is actually rotation by, so what is this rotation? This is I goes to the X goes to minus X. So it's a rotation about should this be X-axis?
Sir,
Huh?
so can we think about the complex number? R is equals to 0 plus iota, means 90 degree.
Yeah, 90 degree. And the only axis involved is the X-axis. No, but the formula is different. No, it's IVI. It's not I times V. So what's happening here? So I goes to minus I, which means QVQ inverse. So
minus I.
okay. So I goes to I. Okay. J goes to minus J and K goes to minus J. Okay, that's better. Is that still okay? J. But that's 180 degrees. So that's wrong. I think I messed it up. So I think what I want to say is this. So yeah, so that was, I took theta to be pi. Now it's okay. No, so here now if I'm doing this, then I'm taking theta to be pi. Oops. Let's write it like this. So then it's okay. Yeah, so I'm sorry, there was I misremembered the formula. Right. So it's actually so yeah, so good we worked out an example. Maybe work out a few more examples. And there's a very nice book. It's by a guy called Kuipers. He talks about quaternions. It's written at a very readable level. And he talks about the applications to astronomy, computing orbits and things like that. The rotation formula, various things in great detail, like all the proofs are. I don't remember the exact title, but it's called Quaternions and some other stuff. But the author's name is Kuiper. Yes, a very nice book. Yeah, sorry. So more questions?
So, sir, it is not related to the quaternions that we are studying here. It is a little bit away from this topic. Sir, it will be basically the eigenvectors of a 3x3 matrix. Um, somewhere I read that, sir, they are the axis of rotation if the determinant is 1. I don't know if I'm right or wrong about this, but when you were discussing rotations, I could remember that eigenvectors are related here. So
So
could you please?
take a rotation, then its eigenvectors are all complex numbers with absolute value 1. So one of the eigenvalues will be 1, and the other two would be complex conjugates.
I don't know if I'm right or wrong about this, but when you were
Please
discussing
mute
rotation,
your.
I could remember that eigenvectors are related.
So
Okay.
take a rotation.
Yeah, so the eigenvalues will be +1 and then cos theta plus I sin theta and cos theta minus I sin theta. Those will be the eigenvalues. See, in two-dimensional rotation, the eigenvalues are cos theta plus I sin theta and cos theta minus I sin theta. The trace is 2 cos theta and the determinant is 1. So those are the eigenvalues. Even for a complex, for a three-dimensional rotation, there's an axis that's the eigenvalue 1, that's fixed. And the other eigenvalues are not real, so you won't see the eigenspaces in real life. Unless it's the identity or something.
Okay.
Yeah, sorry, you had a question.
Sir, you said like these quaternions are will be there in the quantum mechanics. So how I
No, I didn't say that. I said Hamilton's formalism can be used for quantum mechanics, the Hamiltonian mechanics in physics. So that's a completely different, thing that Hamilton did. He showed us how to solve physical systems using something called the Hamiltonian formalism, where your coordinates are given by position and momentum. And later we realized that, you can actually mix up position and momentum spaces and so on. And that is used in quantum mechanics. These could also perhaps come up somewhere in quantum mechanics. There are these Pauli matrices which come when you study hydrogen spin and so on. But I don't really. There is some connection between those but not normal quantum mechanics in three-dimensional space.
Using that shape modeling of robustness implies shape distance somewhat.
Sorry, shape modeling?
Is it this distance between shapes or shape modeling something like?
I don't know what that is. What is that? Sounds interesting.
It's like we have shapes.
Uh-huh.
So we define distance between shapes in topology.
Oh, no, I don't know about that.
Is this formula QV Q inverse? Seems somewhat similar like diagonalization of square images. I mean, yeah, is it somewhat related? Just it seems similar.
Yeah. Yeah, it looks similar, but there you're saying that the result is some diagonal matrix. Here there is, and you're not starting with some, V is not a matrix now, right? So V is a vector.
Write it in terms of matrix.
It's a transformation. It's like V goes to QV inverse. So, yeah, you can write down in terms of matrices. So you expand everything out and you'll get a 3x3 matrix corresponding to the quaternion Q. And that will give you the usual, 3x3 rotation matrix that you derive.
Any more questions, guys? I think we can wind up here. And thank you so much for joining us today. We have many more talks lined up just after this, but we will say a note of thanks to Amritanshu sir now.
Okay. I think there's still something
I'd like to call our beloved instructor, Shubhajit sir, and mentor of the academic self, Shushmita ma'am, and Karthik sir on stage. And I would like to invite Saran sir. Please bless us.
There's still something wrong
Saran,
with
sir,
it.
we want you here to say a note of thanks to Amritanshu sir.
Thank you, Amritanshu.
Okay, always a pleasure.
Yeah, it's always a pleasure to have Amritanshu here. As you saw, he gives very good talks.
With mistakes. I think it's
Oh,
2
it's still
theta.
2 theta?
No, this 2 theta has come here. I mean, I didn't make it.
Okay. Yeah,
So be careful.
right. So it was a very nice talk. Thanks to Amritanshu.
small gift for Amritanshu sir from our side.
Oh, thank you. Very kind.
Yeah. Can we take a picture, sir?
Yeah.
Sounds good. We don't have a photo.
Thank you.
They should also join us.
Hello, sir. Thank you. And we also have a gift for Sarang sir. Please come on stage. And it's quite a blissful moment because Sarang sir is actually the guide of Shubhajit sir. So, yeah, yes.
That's it.
Thank you so much, sir.
Thank you.
Thank you so much, Amritanshu sir.
Thank you.
Thank you. So here we end the first half of our session, and we will be opening the floor for an unmod break for 10 minutes, and then we will be starting again with the speeches by students. Thank you. Okay, yeah.
Karthikeyan, are you ready?
Yeah, I am ready.
அவரால unmute பண்ண முடியுமா? Karthikeyan, are you ready?
Yeah, I am ready. I am ready.
Okay, fine. So in another 5 minutes, we'll begin.
Yeah, we will begin. Yeah, is my screen is visible now?
Good morning, everyone. I hope you all enjoyed Professor Amritanshu's wonderful talk. So let's start with talks from our own students. So the first talk is by Karthikeyan. The title of the talk is Some Sense of Perfection in Mathematics. So Karthikeyan, the floor is yours. You can take 15 minutes to present and then we'll have discussion for 5 minutes after your talk.
Yeah. Okay. Good morning to everyone. My screen is visible now. So I hope my screen is visible.
Yes, it is visible.
Yeah, it's visible. Yeah, thanks. So today we are talking about some sense of perfection in mathematics. So we need a perfection in many kind of things, but we just think about some sense in perfection in mathematics. So that's today's topic. So recent National Education Policy 2022 advocates that students should be a strong foundation skills in language and numeracy, along with the 21st century skills such as soft skills, problem solving skills, communications, and higher order cognitive skills. So this is by a national education policy. So we need some kind of cognitive skills. How one can develop their cognitive skills in like that. So the mathematics is not only solving the problems, is not dealing with only arithmetic, but also some kind of visualizations, patterns like that. So that is today some kind of sense. Okay. So first we are discuss about the perfect square. Then second thing we are going to discuss about the perfect number and perfect cube and perfect rectangle, perfect triangles. So these all are coming under the name called the perfect. So now just think about what is the perfect in mathematics. So anybody have a thought? You can put in chat box also. So what is a perfect in mathematics? What is a perfect? Okay. So I hope something. No, okay, which satisfies all rules of mathematics. Yeah. Thanks, Leela Anand. Okay. Anything? Okay. So most of people think that a subject is already perfect over the years, right? The various researchers have been, found to name perfect squares, perfect numbers, perfect triangles, perfect rectangles, perfect cube, etc. So whatever, finding now, they are using the name is called perfect, which tends to exhibit some form of symmetry. Yeah. Thanks, Rian. Yeah. So think about the list of perfections is a fun. It's not only, fun, some kind of essence is also there. Sense of, beauty in is also there. Okay. So here the, okay, zero construction error. So mathematical things now, here we can, quantify it based on the adjective called perfect. So our doing mathematics, our visualing, our enjoying mathematics can quantify it based on some adjective name is called perfect. So let's discuss some kind of perspective. Yeah. So what is a perfect square? We already know about the perfect square, 1, 4, 9, 16, 25, 36 are the perfect square. Why it is perfect square? We know because its square root is, the integer 1, 2, 3 like that. So this is called a perfect square. So here there are interesting properties is that. So what are the properties? So the square number is basically end with some beautiful properties. A number ending in a 2, 3, 7 or 8 is never be a perfect square. Because, seeing in visualing based on like just think about this is a square. Okay. So number ending with the 2, 3, 7, 8 be the never be a perfect square. Suppose you have a 12. The area of 12 like that, 4, 3. This is never be the perfect square. Similarly, suppose if you have a 100, for example, you have a 100 or 10 by 10. It's sorry, 1 second, 1 second. 1 second. Is it visible now? Oh, sorry. Yeah. Sorry for inconvenience. Okay. So similarly, a number ending in an odd number of 0 is never be a perfect square. So these are the interesting properties based on the number. We just visualize, our visualization is slightly changed to the perfect square. So these all are some properties. There are many more properties. Properties for perfect square is that, like, even number. The square of even number is also the even number. The square of odd number is also odd number, like that. Similarly, the proper fraction. Square of the proper fraction is smaller than the fractions. So square of natural number is equal to the sum of the n odd numbers. These are the interesting fact. These are the interesting fact based on this perfect square. So these properties especially exclusive for only the perfect square. So that's why the number square is called, perfect. We are using the term is called the perfect. Okay. So this the perfect square is familiar to us. We are always discussed with from the school studies. Let's discuss something new. Name is called, the perfect number. What is the perfect number? Anybody can respond? What is the perfect number?
Sum of divisors is equal to the same number.
Yes, exactly. Yeah, it's a perfect number. Yeah. So, for example, we have a 6. We have a 6. For the 6, we have, based on 2, 3, and 2 is also divisor, and 3 is also divisor. 1, 2, 3, and 6. These all are the divisor for the 6. But we just exclude this 6. Suppose if you add 1 plus 2 plus 3, 1 plus 2 plus 3 is equal to 6. So now this is pretty, very rare property for this number. You can choose any other number, the same property cannot come. That's why this number, something specially named called a perfect number. So the definition for the perfect number is a one having the property that sum of its factors, but excluding the number itself. Okay, so the total sum of the factor excluding the number itself is equal to the same number. So this is called the perfect number. Okay, let's think about the perfect number. So how many perfect number for 1 to 10? Anybody can imagine? Any response? Any chat box response?
1.
Okay, 1. Yeah, it's interesting. Oh, 4. She told about the 4. Let's, it's very simple now. Just try about. For example, you choose 8 now. What are the divisor for the 8? So 1 is divisor, 2 is divisor, and 4 is also divisor, and then 8 is also divisor. Okay, 1, 4, 2. Just add, remove the 8 and add 1 plus 2 plus 4 is not equal to 8. Therefore, 8 is not a perfect number. Similarly, you can, think about the perfect number from 1 to 10. It's very small elementary work, but interesting now. There is only one perfect number between 1 to 10. There is only one perfect number between 1 to 10. Okay, let's think about, it's okay. Let's think about the 28. The 28 is the next perfect number. The first perfect number is called a 6. The next perfect number is a 28. And third perfect number is a 496. There is a huge gap is there. There is a huge gap. 6 is first one. Next one is 28. And third one is 496. So there is a huge gap. So what about the fourth perfect number? The fourth perfect number is 8,128. So what? This is a very huge gap, too big gap. So that's a interesting thing. Okay. So nowadays there is a computer, many digital computer is there, many opportunities there. Still now we have find out only 51 perfect number. Only the perfect number is a 51 perfect number. Okay. So can we predict next larger perfect number? Anybody respond? Trying to predict next large. So far we discuss about 8, 1 to 8. 8, 1 to 8. Okay. So anybody guess the next perfect number? Next larger perfect number?
Around 30 million.
Huh? 30?
Around 30 millions.
Okay. Yeah, it's good. Okay. So that is, unpredictable things. We have to, work it out and solve how many factors is there and add up to our number is either come or not. So this kind of work we have to do. So far we find only the 51 perfect number. This is start from the ancient Greek periods. So this perfect number concept start from ancient Greek periods. And So they are start from 6 and 28 like that. Okay. So now let's think about some kind of conjecture. So see the pattern. Here the 6 is there and last digit is 8 and last digit is 6 and another one is 8. Can you guess any, can you pose any kind of conjecture? Like, anybody try it out? Yeah, I cannot see the chat box actually. Okay. Okay, number ending with 6 or 8. Okay, Leela Anand say about. Yeah, it's interesting. A number ending with 6 or 8 may be the perfect number. Okay, so we can, remaining numbers we can leave it and just discuss about, just see the pattern of the number and look at wherever the 5-digit number has end with 6. Just try about that 6 and 8. Similarly, we can do the conjectures. This is a one kind of conjecture. And anything, some other conjecture? Anybody try some other conjecture? Okay. So perfect numbers must end in 6 or and 8 alternatively. So this is one kind of conjecture. And second, one perfect number between 10 to 100. I mean, here, the 2-digit to 3-digit, for the 2-digit to 3-digit, there is only one perfect number. So this is one kind of, conjecture. Similarly, we can increase, we can, think about the conjectures and increase our conjectures is also there. Okay, there is only perfect number between. Sorry, I cannot see the chat box along with my presentation. Okay, here is the chat box. Okay. Okay, the gap between two successive perfect numbers will be growing exponentially. Yeah, exactly. So that is one kind of conjecture. And there is only one perfect number for 1 digit and 2-digit, 3-digit. Exactly. So that's what I am telling to convey. Yeah, that's good. And number ending with 6 or 8 alternatively. Yeah. So here I put the word called alternatively. Yeah. The next perfect number, last digit will be 6. Yeah. Okay. It's good. But we can find out the next 52. Yeah, exactly. So this is also the open-ended questions. Till now we are finding out 51 perfect number. We can, this is an open-end question. So whether the 52th perfect number exists or not. Suppose if it exists, we just find. Suppose if not exist, we have to prove it is not exist. So this is the largest perfect number like that. So we just close the perfect number like so that. 4 is not perfect number. Okay. Thanks for your interesting response. Yeah. Now go to another topic. So perfect cube. So may everyone know about the perfect cube because the perfect cube is start from school standard onwards. So the beauty of perfect cube, the cube of a even number is even. So even number is even. So that is one kind of beautiness. It's not know about algebra, graph theory like that. It's very simple. Work with numbers. That's all. So these are the interesting property for the perfect cube. Similarly, the cube of odd number is odd, and some consecutive sum of consecutive odd numbers a perfect cube can express. So this is also interesting property. So there are many kind of properties is also there. Okay, let's go to the perfections in triangles. Anybody tell about what is the perfections in triangle? Anybody think about the perfect in triangles. We know the regular triangle, irregular triangle, but what is a perfect triangle? Anybody think? Can respond. Angle is 180. Equilateral triangle. Yeah, exactly. Okay. Equilateral triangle. All equilateral triangle is a perfect. Something new property, some beautiness, some more beautiness needed. Okay, all sides and angles equal. Okay. Okay, all sides and angles equal. So that's interesting. Yeah, perimeter equal to its area. Exactly. So that's a property. So the people are perfect triangle. The definition of perfect triangle is the perimeter. Perimeter and okay, the sum of two sides must be greater than third. Okay, okay. So that's a natural property actually. Okay, perimeter is equal to area. Then it is called, perfect triangle. So similarly, perfect rectangles is also same. Perimeter, both perimeter and the area is equal to same. So yeah. How one can, prove perimeter equal to area? So perimeter we know sum of all boundaries. Suppose the triangles, we have 3 boundaries, add up to equal to its perimeter. Okay. So one interesting now, here the 5, 12, 13. So this number of, this is a Pythagorean triplet. This is a perfect triangle. For example, the perimeter equal to 5 plus 12 plus 13. So add up to 5, 10, 30. So this is the perimeter. And what about area? So here area is 5 into 12 divided by 2. Because half into base into height, na. That's a formula for triangle. So 6, 5, 6 are 30. So area is equal to 30. So this is interesting property and very rare for triangles. That's why this is called perfect triangles. This is not okay for not all triangles. Some triangles is exceptional. That is called perfect. So for in right angle triangles, there are only 2 triangles is there. One 6, 8, 10. One is 6, 8, 10. This is a Pythagorean triplet. And another one is called 5, 12, 13. So these two are interesting property in perfect triangles. Okay, let's discuss about perfect rectangles. The same content for triangle extended to the rectangle. So perfect rectangles are those whose areas are numerically equal to their perimeters, whose areas are numerically equal to the perimeters. So one beautiful perfect triangle is 3, 6. The length 3 and breadth 6. Suppose this is the length. So 6, 3. So either we can do it. So this is also 6. This is also 6. So perimeter equal to add up to 3 plus 6 plus 3 plus 6. 100. 18. So what about area? Area equal to L and B. So 6 is 18. So that's all. So this is a perfect rectangles. And another one perfect is same as a 4, 4. Length is 4, 4. It's naturally come with, end with square like that. Okay. So this is the perfect triangles and perfect rectangles. This is also still open-ended questions. Is there more perfect triangles is available or not? We can, this is a interesting idea. These kind of things explore our mind also. Okay. So I have got these ideas from these books as Math Wonders and some 2 articles. 2 more article is there. Okay. This is some interesting property. The formula for the perfect number 2 power k minus 1 and 2 power k minus 1 times of 2 power k minus 1. So this must be the perfect number. Okay. Any questions regarding the perfection in mathematics? Here we are discussing on some sense.
Thank you, Karthikeyan, for the wonderful talk. So if there are any questions, you can ask from the audience. If not, then let's thank the speaker and then thank you so much, Karthikeyan. It was a wonderful talk.
Thank you. Thanks a lot. Thank you.
So our next speaker is Jaydev Deshpande. He's going to talk on sampling distributions for stratification in object detection problems. Jaydev, are you there?
Yes, I am here. I trust I'm audible. Let
Yes.
me also share my screen. Right. Okay, is my screen visible as well?
Yes.
All right. Shall we begin then?
Yes, you can take 15 minutes and then 5 minutes for discussion.
Okay, great. So the idea of this talk is that typically when it comes to object detection or any sort of, say, computer vision problem, most of the base models that are trained in this domain, they are trained on very large data sets, like you might have heard of things like ImageNet, for example. But when you apply them to specific problems for research or for business or whatever it is, typically the training data that you get for that problem is relatively small. For example, if you wanted to make a self-driving car and you wanted to start with something that is trained on ImageNet and apply it to making a self-driving car. Now, the data available for self-driving cars may not be as large as the data that was present in ImageNet. So what you need to do is you need to first of all do something known as transfer learning. And the idea is to be able to extract maximum amount of learning possible from a relatively small data set. And the idea of this talk is to see what we can learn from the annotations or the labels of this training data so as to exploit the maximum possible learning out of the model. So let's get started. Basically, let's simply do a quick revision of what are the different types of problems in computer visions. I'm sure all of you know this, but I'm building up to something which we'll see. The simplest type of a computer vision problem is simply image classification. Let's say this F is your model. You simply feed it an image and it gives out a class. It's a particular label. It's a classification problem. So for every input, there is one specific class. So, you give out this particular image, says that 60% probability it's the image of a cat, and with 40% probability is the image of a dog. So this is essentially a binary classification problem. This is what you call a binary classification problem, which means that your output label can only belong to a set of exactly two elements. So it has to be one or the other, and they are mutually exclusive and collectively exhaustive, right? The next, when you add a little more complexity to the same problem, we get actually the object detection problems, where you give an image as the input and the output is significantly more complex than this membership probability distribution. You have to be able to detect certain objects in the image and you have to be able to detect where they are. So you see classification plus regression. It's sort of a combination of both of those things. And then finally, one of the more complex problems in computer vision is what is known as semantic segmentation. So every single pixel has to be qualified, has to be separately classified. So, and then depending on how you group those pixels together, you can sort of start counting objects. So you see that this is an image and every single pixel of it has been first classified into foreground or background. And then, depending on how you group certain foreground pixels together, you can count different types of objects. So there it is. You see what happens is you start with a simple classification problem, which is a binary or a multi-class at best, where the output is supposed to be a probability distribution over a finite set, right? From that, it goes to something that acquires a regression component, which is you first of all identify the fact that there are 4 regions, 2 of them are faces and 2 of them are hands, and then you try to regress, the corners of the bounding boxes, which tell you where exactly a certain object is. And then finally, for each pixel, you can produce a class. And it doesn't even have to be 2 classes. It can be multiple classes, right? So it doesn't have to be just this blue pixel or black pixel. It can be multiple things in between as well, right? So this is how the landscape of problems in computer vision is. Pretty much everything you do in computer vision is going to sort of boil down to these type of problems one way or another. The question is, why do we generally stratify when we are trying to, build classification models or even regression models in some extent? Well, first of all, we want to be fair to our model. We don't want to ask it out of syllabus questions. So typically, if you think about it, those of you who are the BS students in this program, the examples or the illustrations that are shown in our video lectures, they are typically the training data. We watch somebody solve the problem, we try to solve it ourselves, and we convince ourselves that it's fine, we have learned something. And then there are practice assignments. That is something called as validation data. So that you try out practice assignment, you see that most of them you get right, some of them you get wrong. For those that you do get wrong, you go back and you try to update your learning. And then finally, when you appear for the graded assignments or the end terms or the quizzes, that's the testing data. Then no learning comes out of that until unless you're, of course, unfortunately repeating the course or something like that, which I hope doesn't happen too much. The idea is that you stratify problems that you present to the model in proportional ways across all of these things. For training data, whatever is the distribution of the problems that you have is the same that you have in testing data as well as validation data. But here's the problem with stratification. As prediction tasks become more and more complex, stratification becomes difficult. So let's say if you just wanted to stratify a cat versus a dog kind of a problem, then that's easy. That's like tossing a coin. Let's say that, in my training data, cat versus dog, that problem is essentially a Bernoulli variable with some parameter p. We'll find the value of that p, and we'll ensure that in the testing data, the value of the p remains the same, right? But as the task evolves, like for example, if you have an object detection problem where classification is also there, regression is also there, how do you stratify? It's not easy, right? So the idea is that the variable y, which is the true labels of your training data set, it starts acquiring additional attributes. In simple binary or multi-class classification, the attribute is simply membership, into a certain class. Y is either a cat or a dog. If it's not a cat, it has to be a dog. But if it's a multi-class problem, then Y is one of a finitely large set of values. Like in the iris data set, for example, Y has to be a member of exactly of a set which has exactly 3 elements in it. So it can have any positive integer as the cardinality of that set, and it will be specific to those things, right? So training labels are essentially a joint probability distribution on a set of RVs. Now, what I'm saying here, this is my hypothesis. This is one way to look at the training labels, and we'll see how that actually helps in stratification and exploiting the maximum possible learning in a specific object detection problem. So we say that binary classifications, the labels are simply a Bernoulli random variable. This is obvious. For multi-class, they are categorical random variables, right? Or you can also say that they are uniform discrete random variables, or they could be binomial random variables, whatever the case may be. But what about multi-label problems where each input can have any number of outputs and any of the outputs? So this is like sampling something from a set with replacement, including the possibility that no sample will be drawn. What do you do with bounding boxes? Because bounding boxes have an element of coordinates to it. So that becomes a regression problem on top of an original classification problem. If you're actually driving a self-driving car or training a self-driving car, you need to figure out whether an object in front of you is another car, is it a pedestrian, or is it a cycle, or is it a two-wheeler, for example. So that's like the classification problem. At the same time, you need to be able to figure out how far it is. So that's a regression problem, and you need to solve both those problems simultaneously. So how do you stratify such data sets? That's basically the point of this talk. And my proposal is that we imagine this training data as, or especially the training labels, as a joint probability distribution over a set of random variables. What are these random variables? Let's take a look. Stratification essentially means that ensuring that the distribution of these random variables in the training subset is very close to the distribution in the testing subset. If they are widely different, then essentially you're asking the model to solve out of syllabus problems. Let's say you train a self-driving car within the IIT Madras campus. It's very unfair to expect it to perform well outside the campus as well, right? So we can't do that, which means that whatever random variables make up the distribution of the data inside the campus is very different from the corresponding random variables, the way they behave outside the campus, which is again that the model, there's no way the model can generalize that well. So let's see what happens. Like, you have a binary classification, the problem, and the labels could simply be cat or dog or whatever. It's a Bernoulli distribution, straightforward. In multiclass is just a generalization of the binary. Instead of tossing a coin, you're now throwing a die, right? So any set of fixed set of values is possible. So you can have a uniform discrete distribution, a binomial, or a categorical distribution. And this is the interesting thing. So object detection problems usually fall in the multi-label category. Every image can have any number of any type of class. They can have nothing also. So for example, you can have a cat or a dog or a human. You can have a cat or a human. You can have nothing at all. You can simply have dogs. You can have multiple dogs, whatever the case may be, right? So these are highly compounded random variables called multinomial variables or Dirichlet variables, as we'll see. And which of them do you pick for a given problem, and how do you stratify based on them? So here's what the training labels for an object detection classification problem looks like. So typically Y just looks like this for a Bernoulli, for a binary classification problem. It could look like this for a multi-class, it could look like this for a multi-label, but for an object detection problem, Y looks like this. So you see that it's actually a list of 2 dictionaries, and each dictionary has 2 keys, boxes and labels. So the boxes are essentially the corners of the bounding boxes, and the labels are for that particular bounding box, what is the label? So essentially this particular dictionary tells us that there are 3 boxes in a given image. 2 of them are bottles, 1 of them is a laptop. In the second image, we have 2 boxes, 1 of them is a bowl, 1 of them is a cup, right? And that is the kind of stuff that you see here. So how do you capture the idea that this is a bowl? You find the coordinates of that triangle, and then you give it a string label, right? How do you stratify this? Like, let's say I had to split this data between training and testing, assume that there are many more such entries present. How do I stratify them such that the representation of all types of objects of all sizes is equivalent in both the training and the testing set? This is a highly non-trivial problem to solve. And as far as I know, there isn't a straightforward method to solve it. So what we are going to do is try out some hacks, some empirical experiments to see how well it works. So this is what I did in order to be able to solve, to see how much of these empirical distributions help us in, stratifying the data well. This is the experiment setup. I took 3 different data sets, and for each of them, we do 2 types of, but isn't these coordinate depend on the orientation of the object kept? Yes, absolutely. No reason that it should exactly be rectangular. You can have an oblique rectangle also, no problem. Right. So yeah, there is no reason that they have to be perfectly rectangular either, Ravina. All right. So we are going to do, what I did when I was preparing for this is that I did 3 experiments on 3 different data sets of varying complexity. One data set was very homogeneous, very little background changes, very specific problem to solve. And the other one was very noisy at the other end of the extreme. So we do 2 sets of experiments for each data set. Each experiment involves 40 experiments, 40 sessions of training and testing. And in the first set, we do a random 60-40 split, right? The key being that these are random 60-40 splits. And in the other set, we apply some suitable stratification logic and do the random then stratified 60-40 split again. We do 40 experiments in one set, we do 40 experiments in the other set, and we see if the accuracies are comparable, right? And for each experiment, each of these 40 experiments, you start with a blank PyTorch implementation of fast RCNN, which is an object detection model, trained on the ImageNet dataset, right? So we train exactly for 20 epochs, find the average scores. The score method in this, the metric in this case, is something known as map of IOU, which stands for mean average precision of intersection over union. We'll go into the details of what this means if you have time later. And all the other hyperparameters are kept the same. For the random split and the stratified split, we keep exactly the same hyperparameters, and the model starts from exactly the same baseline. So we know that the comparison is actually fair. So what happens is that you end up with 40 scores for the random splits and 40 scores for the stratified splits. And then we compare the 2 and see which one gives us better results. And note that all of these data sets are relatively small, because that's how typically people introduce problems to you. So especially when you're talking to clients or customers, what they want to know is that given the smallest possible data set, because I'm not yet in business with you, so I'm going to give you the smallest possible data set, tell me what's the best you can do with that. So these are all images with not more than 200 images each, and ImageNet, as you know, is tens of thousands of maybe even hundreds of thousands of images. So let's see, the first problem was this chess pieces data set. where you have about 202 images of various types of chess positions. These are not valid chess positions because, as you can see, that there is this board with a single black queen on it. There is no way that this is going to happen in a game of chess which is valid. So these are simply, images of, these are not captured while somebody is playing. These are just, there is a chessboard, people keep pieces on it and take a picture. It's a very homogeneous data set, by which I mean that the camera angle and, the brightness and the background is all very uniform. It's only the pieces that are moving. So this is a relatively easy problem to solve because most of the learning just focuses on the pieces itself, right? It doesn't have to bother about separating out what is the background, what is the foreground, none of that, right? So when you do the random split, it turns out that we get a score of 0.4. The map IOU is 0.4, average of 40 runs. And these are the two types of mistakes that it made most frequently. Once you get the score, you find those images which have the worst score, and then you try to infer mistakes from that. So it almost always gives false negatives for single pieces. This green box indicates that this is the ground truth, it's there, but there isn't a corresponding predicted box there, which means that a bishop, this is a black bishop, a white queen, and a black queen. So typically bishops and queens, if they are appearing by themselves in the image, the model simply fails to recognize. So the obvious solution is that, stratify by the number of pieces on the board, and this actually reduces the performance by 1%. So from 0.4, you want to 0.39. Which is again, very counterintuitive, because if we wanted a strategy to stratify this data set instead of random sampling, you would simply say that, okay, since it is making false negatives, it is producing false negative for single pieces, there's no way that I should not be stratifying by the number of pieces. But if you look at sort of the number of images or which have across the number of pieces on the board, you'll see that out of those 202, almost half of the images, 100, have exactly one piece on them. And the rest of them could be anywhere between, say 2 to 32, right? So this is a unique opportunity. We don't need to employ random variables here. We can simply say that if collect all the images that have exactly one piece on them, and that becomes a multi-class classification problem, right? So treat that separately as a multi-class classification problem, and the rest then you stratify separately by how many pieces are present. And when this strategy is applied, we get a 6% increase in the map of IO, which is statistically significant. And how you test that is you do a one-sided t-test with the alternative hypothesis that one group of scores is higher than the other. The average of one group of scores is higher than another group, and that passes at 95% confidence interval in this particular experiment. So you get a 6% statistically significant increase. So this was a very simple, non-parametric, empirical way of stratifying your data set, which actually gives you a pretty good boost, given that it's a small data set. The models aren't doing something drastically different. And you see that the train test split, which is 60-40, is kept very close to 50-50 because we want to be very strict with the model. We want to ensure that the maximum possible learning is actually extracted out of the least possible number of samples. We could have gone with 50-50 also, but we don't want to be unnecessarily unfair or unnecessarily strict with our model either. The second experiment we tried was this pedestrian detection task. So this, you see, this first column is the ground truth. Sorry, it's actually the input images. And this middle column is the mask. So these particular regions, they are called masks. They are, that is essentially the label. And these are the ground truth. So, and this is what the model predicted. The third column is what you see. This is what the model predicted. Can you see what the model is getting wrong? Any guesses? This is the ground truth, the middle column. And the third column is actually what the model ended up predicting. What would you say are the mistakes it is making? Anyway, you see that it's detecting people in the back. It's detecting all the people, but you see the point is pedestrian detection. So this fellow, the person who's walking here, is the pedestrian. This little person, well, not little, but this small figure that is in the background is not a pedestrian. So the entire point of this exercise is to be able to separate them, right? Now here do you see that there are 3 people on the road, the rest of them are crowded near a shop. Again, there is one person here, there are 2 people sitting on the lawn. So what the model is learning is to simply predict, it's simply learning to predict people. It's not figuring out how to detect pedestrians, right? So again, this data set was fairly small, only 170 images. The random split score was 50%, 0.5. Too many false positives, as you can see. The people in the background are being detected, lots of them. And the foreground, the false positives are usually small. Pedestrians tend to be the largest object in the image, and whatever else it is predicting are typically small. So what sort of a stratification strategy can be applied here, which could help us? So you see what happens is that if you simply count the number of pedestrians per image, that follows more or less a Poisson distribution. Now what we can do is once we fit this Poisson distribution well, and it actually does fit well, you can do a chi-square goodness of fit test and see that the number of pedestrians per image is more or less a Poisson variable with fair enough confidence. Now from the same Poisson distribution, you can sample the train set and the testing set. And since they're sampled from the same distribution, there's no way that they will deviate, right? So that's a proper stratification. The other aspect of what the model gets wrong is that it gets the size of the people wrong. So you create another random variable y, which is size of the pedestrians relative to the image. And that follows a log normal distribution. So essentially you count the number of pixels that is there in the foreground for a pedestrian and divide that by the size of the image itself. That gives you some fraction. So you see that most people are around 10% of the image they occupy, right? Very, very few people will occupy 20%. And then, this is basically a KD plot of the training and testing values for the y random variable, which is the fraction size of the foreground mask. And you see that this follows a log normal distribution. There are normality tests for that also, which also pass with fair enough, confidence. Now that you have these two random variables, how do you use them in stratification? Remember that every image that comes in has a particular value, a particular probability on this random variable as well as this random variable. So now this becomes a joint probability distribution. So the set of images is essentially a distribution over the joint probabilities of these two specific random variables, right? And this is basically the joint probability distribution of x and y. You see that, well, actually it's not a probability distribution, it's more like a contingency table. But if you divide this whole thing by 170, you will get the joint probability distribution. So area of the mask goes from 2% all the way up to 20%. And these are the number of images that fall within that particular cell. As it's also stratified by the number of pedestrians. So how do you stratify given this distribution? For each cell, so one pedestrian and the area of masks is between 0.17 and 0.18. We have two of them. So each cell you can divide into 60 and 40, right? And all of the groups of those 60 divisions go into the training, all of the 40% go into testing. So that's one strategy of doing that. Note that in this particular case, you can't straight away stratify this because there are certain boxes that have exactly one, and that you can't split it. Either has to go into training or it has to go into testing. So in order to fix that, what you can do is simply adjust the edges of the bins such that each box has at least two images in it. That way, stratification will work, right? Now, when you apply this strategy, you get an additional 3% gain on the random scores. But this 3% is not statistically significant, right? But the good news is that the variance of this is much low. So it's very tight. If you look at the stratified split scores, it's very tight, whereas the random ones are, a little more broad, although they may have a lower average. What this means is that the model is actually reaching its limits. So is there a random split which performs better than this? Yes, but those are very, not very likely, not likely enough, right? So this is another way where you can, express the annotations present in an object detection data set as a combination of random variables, stratify those random variables and come up with a better solution. Finally, the third experiment that we did was on a subset of a data set known as MS COCO, Microsoft COCO. COCO stands for Common Objects in Context. Lots of images. I just took a subset of which contains common kitchen objects. So things like cups and things like bowls and apples and tables and stuff like that. And again, same thing, we do a random score, random split score. It's 0.3, which is, by the way, not bad entirely, given that the model was almost always trained on ImageNet. It almost never recognizes apples. Any flat surface, it thinks it's a dining table, and it fails to recognize small cups. So how do you stratify this? Again, if you look at simply the count of objects that come here, apples is the rarest class, dining tables and cups. Yes, sorry.
Can we quickly wind up?
Yes, give me another minute maybe. Yeah. So the dining tables and the cups, two of the categories belong to the most frequent classes, and the third mistake belongs to the rarest class. So it's obvious that again you should stratify perhaps by the number of apples or the number of knives, carrots, bananas that appear in each image, which could be zero also, right? So that's one way of doing this. So ultimately you can simply take a subset of three variables. X is a variable that denotes the number of apples, Y denotes the number of cups, Z denotes the number of dining tables. Now this is a bit tricky. Most images are not likely to have multiple dining tables, right? So simply whether it is there or not could be a Bernoulli variable you could think of. So this is slightly misleading. You might have to actually try it out to see what happens. But then again, it doesn't take size into account. And you see that when we look at our mistakes, it's like small cups matters, large dining tables, they matter. So again, this actually doesn't give us any improvement. But if you look at the sizes, because now since we had XYZ contain the number aspect of things, we have nothing to capture the size aspect of things. So what you can do is simply find histograms of the 8 types of objects, and you look at the dining table. So you see it's a strongly bimodal distribution. Basically what this means is that you can simply have 2 types of dining tables, either large or small, right? So that gives us another Bernoulli variable. And when we actually split by this, in addition to the earlier random variables, when we include these 4 types of random variables, which is number of objects and size of dining variables, being a Bernoulli variable, small or large, we get a statistically significant improvement of 2%. 2% in MS Coco, by the way, is enough to make you jump hundreds of places on the leaderboard. So this is significant, actually. Right? So there it is. The idea broadly is that we can always do better than random splits. Random splits does not mean fair splits. This is something that we have to keep in mind in object detection problems. And how do you do that? You find the mistakes that the model makes and see if the mistaken aspect is representable by some random variable which you can mine from the data set. Then you estimate a joint probability distribution over all of these mistaken aspects and then train, sample the train and test splits from it. That's broadly the idea. There is a detailed blog post here which you can read. And at the end of the blog post, there is a link to a GitHub repo which contains the code for all of these things. Do try it out. It's not, the code at least is not very well documented, but if you do run into any problems with it, please reach out to me over here. Thank you. I'm happy to take any questions depending on how much time we have.
There's one question for you. Not exactly question, but the JPD which you got for X and Y was very sparse. You
Yes.
can use auto encoding for that to improve, less number of perceptrons in your layer.
Yeah, but I don't have the luxury of being able to choose my architecture. My architecture is already dictated by fast RCNN.
Yeah, the RCNN,
I can't go and mess with that.
Yeah, if you use Keras instead of PyTorch, then you can define number of perceptrons in your dense layers.
No, but that correct. But then I'll have to redefine the entire RCNN architecture. Right? Yeah, that I not worth time more. And here's the thing: if I do that, what happens to my transfer? It's already trained on ImageNet. Like if I simply knock off certain neurons in it, the learning is lost. Which means that this tiny data set of simply a few hundred images, it'll actually make things worse for me.
Okay, and why you choose PyTorch implementation instead of others?
No reason at all. Just because actually I'll tell you why. This is the standard tutorial you'll get in PyTorch for object detection. That's it. I just started from that. No reason. Absolutely doable in Keras or raw TensorFlow if you like.
Thank you.
Thank you, Jaidev. So if you have more questions, maybe you can reach out to him directly. He has already given you the email ID. That was a wonderful talk from Principal Data Scientist. Am I right?
Yes.
Yeah. So maybe we can introduce ourselves and then start talking, right?
Oh, I'm so sorry. So I am a principal data scientist at a company called Gramener, and I'm about to enter my degree level. I just finished both my diplomas. I'm about to enter the degree level.
Awesome. Okay. So thank you, Jaidev. Thank you for the wonderful talk. Karthikeyan, sir, are you there? Karthikeyan SS, the one who gave the previous talk. I guess you're here. I can see your name. Okay, fine. So I just wanted to ask him what he's currently doing. Anyway, so let's move on to the next talk. There's a slight swap in schedule. We'll just finish Sona Jhuri Maitra's talk, and then we'll go to Rajkumar's talk. So, Sona Jhuri, are you there?
Yes, ma'am, I'm here. I'm audible, right? If you can kindly
Yes,
confirm.
you are perfectly audible. She is going to speak on introducing elliptic curve and its applications in cryptography. So can you please introduce yourself and then start the talk? You have 15 minutes to talk and then 5 minutes of discussion after that.
Sure. I'll just present the slides and I'll start.
Yeah,
Okay.
sure.
Ma'am, my screen is visible, right?
Yes,
The
yes,
presentation is visible?
yes.
Yeah. Okay.
So
So
you
good
can take up to maybe 12:35.
Okay. Okay, sure.
Yeah, means including discussions.
Okay. So good afternoon, everybody, my respected professors, instructors, and fellow participants. A short introduction about myself. My name is Shonajuri Moitra, and I am currently a second-year undergraduate student of Computer Science Engineering from Heritage Institute of Technology, Kolkata, and I am currently in my diploma level at IIT Madras. So today I'm going to speak on the topic introducing elliptic curve and its application in cryptography. This is a brief outline of the presentation. The presentation can be divided into two parts. At first, we're going to talk a little bit about elliptic curves. We are going to see what the Weierstrass normal form is. We are going to take a look at singular and non-singular elliptic curves. And finally, we are going to define a group operation on an elliptic curve. The next part of the presentation will deal with the application of elliptic curves in cryptology. We will start with a brief introduction to cryptology. Then we will move on to the elliptic curve discrete logarithm problem. We will discuss about the Diffie-Hellman key exchange, and finally we will see what the insecurities of the elliptic curve discrete logarithm problem are against a quantum adversary. Okay. So let us start with elliptic curves. Let us start with what an elliptic curve is. So as you can see, this big equation with 10 coefficients here, this is an equation of any general cubic curve. Please note that all the coefficients here are rational coefficients. However, any general cubic curves can be transformed into an elliptic curve, which is y square equal to x cube plus x square plus bx plus c. And this form is called the Weierstrass's normal form of cubic polynomials in two variables. So we are basically transforming this big equation into this equation. And this equation is basically the equation of an elliptic curve. So there are two types of elliptic curves, singular elliptic curves and non-singular elliptic curves. So elliptic curves are basically cubic polynomials, right? So we know that it will, when we equate it with 0, there are supposed to be 3 roots. So in singular elliptic curves, we have repeated roots. So in case of 3 roots, we can either have roots in which all 3 are repeated roots, all 3 are the same roots, or we can have 2 repeated roots, another distinct root. For non-singular elliptic curves, we will have all 3 of the roots distinct. So we can see from the figures here, these are examples of singular elliptic curves. So this is called a cusp. Here you can see at this point, all 3 roots of the elliptic curves are repeated. Okay. And for case of, in case of node, we have 2 roots repeated here, and this root here is distinct. In case of non-singular elliptic curves, again, we have 2 diagrams. In this case, we have 3 distinct real roots. See, they are intersecting with the x-axis. One root here, another root here. I hope you can see my cursor. And in this case, we have 1 real root and 2 imaginary roots. Like imaginary roots will always exist in pairs, right? Because we are taking rational coefficients. So if we have, if we have 2 imaginary roots, then we will have 1 real root. So generally, we will talk about non-singular elliptic curves because the group operation on non-singular elliptic curves are interesting. So we will move on to group operation. So before defining the group operation on an elliptic curve, let us have a brief introduction about what exactly groups are. So in mathematics, a group is a set on which a binary operation is defined. So any two elements of the set is operated with a binary. Binary operation means two operands and one operator. So its group is basically a set over an operation, and that set over that operation will fulfill some criteria: the closure property, the associative property. The entire group will have a unique identity element. For example, say if an element of the group is say P, and say an identity element exists, say E, in the group. So if we operate P with E, then we will get P. That is meaning of identity. And every element of the group will have an inverse. So again, let us take for example P, an element in the group, and say P inverse exists in the group. So if we operate P with P inverse, we will get an identity. And please note here that identity is unique to the entire group and inverses are unique to each element of the group. Now that we know what groups are, let us define a group operation on elliptic curve. Now, group operation of elliptic curves are interesting because they are defined geometrically. So it's minute. Yeah. So group operations on elliptic curves are defined geometrically. So we need to visualize it. So this is an elliptic curve. Say we take 2 points P and Q on the elliptic curve. Now, how will we define the group operation? The group operation is defined by the plus operation. Please note that the plus is not our traditional addition operator. We are just defining an operation plus. So if we take 2 points on the elliptic curve P and Q, we draw a line through P and Q, and it will cut the elliptic curve at another point, because this is a cubic curve at the end of the day, right? So if we equate it with a line, I mean, if we pass a line through P and Q, it has to cut at another point. It will cut at 3 points in total. So this P star Q, now we are talking over rational numbers. Okay, so if P and Q are rational numbers, then P star Q, that is the third point in which this line is cutting the elliptic curve, will also be a rational point. Okay, because this is a rational line, this is a rational curve. Also, if you think it algebraically, when we are equating this cubic polynomial with a straight line, okay, what is the equation of a line? Y is equal to mx plus c. So when we are substituting this equation of the line in the elliptic curve equation, y is equal to this equation. Let me just go back here. Y square equal to x cube plus ax square plus bx plus c. We will get a cubic equation, and it will have 3 roots again, because all cubic equations has to have 3 roots. And if 2 roots are rational, then the third root has to be rational. Now, the group operation is defined as P plus Q, and until now we have reached P star Q. Now, how we will get P plus Q from P star Q? We will drop a perpendicular. And kindly note that elliptic curve is symmetric about the x-axis. That is, above the x-axis and below the x-axis are same. So it is basically the mirror image. So when we drop a perpendicular from P star Q, it will cut another point P plus Q, which will basically be the mirror image of P star Q. So if P star Q is say x comma y, then P plus Q will be x comma minus y. And this is how the group operation is defined on an elliptic curve. Now let us verify if it is satisfying all the properties of a group. We will check for rational numbers. We already saw the closure property that if P and Q are rational, then P plus Q will also be rational. Why? Because P plus Q is the mirror image of P star Q. We saw that P star Q is rational. So if x comma y, both the points are rational, then x comma minus y has to be rational. Then we will check for associative property. Here you can see another a diagram of closure property. We have taken points P1 and P2 in consideration. For associative property, what is associative property? This one. P plus Q plus R in closed braces is equal to P plus Q in closed braces plus R. Now this computation is a bit tedious, but we can do it. In a similar way, we will take 3 points P, Q and R, At first, we will compute Q plus R. How will we compute Q plus R? If we take, say, 2 points Q and R, then at first we will find Q star R by joining it with a line. And then we will find Q plus R by taking the mirror image of Q star R. And then again, we will do the same thing. The point that we are getting, Q plus R, we will do P plus Q plus R. And then for this is the LHS. For the RHS, we can also do the same thing. At first, we will do P plus Q by taking P star Q and then by mirror imaging it about the x-axis, and then again computing with it with R. So it is a very tedious calculation, so I didn't show it here, but you can easily verify it. So we are done with closure and associative. We are left with identity element and inverse element. Now these are very interesting actually. We will assume that the identity element lies at infinity and infinity lies on a vertical line. These are axioms of another branch of geometry called projective geometry. Now let us verify that if the identity lies at infinity. So about identity, for an element P in the group, if we compute it with identity, we will get back the same element. So let us verify it in this case. So if the identity is lying at infinity and infinity is lying on vertical line, so say in this case, when we join Q and infinity, we will get a vertical line, and we need to have 3 points. So when we join Q and infinity, or the identity element and infinity, say O, when we join Q and O, we will get minus Q. The vertical line will cut the elliptic curve again at minus Q, the mirror image of Q. And now minus Q here, if you think a bit, then minus Q is P star O at the moment. Minus Q is P star O. And then when we mirror image it, we will get back Q. And this will satisfy our criteria for identity element. When we are computing Q with identity, we will get Q. Similarly for inverse, you can see the same thing. If we compute Q and minus Q, so Q minus Q will be the inverse of Q. So about inverses, if we compute element and its inverse, we will get back the identity, right? So if we compute Q and minus Q here, if we join a line joining Q and minus Q, it will be a vertical line because mirror image, right? And by projective geometry, we know that identity will lie on a vertical line at infinity. So when we compute Q and minus Q, we will again get O, or the identity which is lying at infinity. And then if we mirror image it, we will get minus O, and minus O is equivalent to O. So we are basically getting back the identity element again. So the inverse, that the thing that we told for a group, that if we compare that each element has a unique inverse, which will give back the same, which will give back identity on computation with the element, is also satisfied here. So we have verified it for rational numbers. So that is the group operation on elliptic curve. Also, the plus operation here, the plus operation that we define geometrically, satisfies the commutative property. What is the commutative property? That P plus Q is equal to Q plus P. You can also verify it, that if we join, I mean joining points P and Q and joining points Q and P are the same things, right? And the groups which satisfy this property, the commutative property, along with the other four properties, that is closure, associative, existence of an identity unique to the group, and existence of inverses unique to each element of the group, we call such groups abelian groups. So this group operation that we defined on non-singular elliptic curves is an abelian group. So we are done with the first part of the presentation. We have learned what elliptic curves are. We have learned how to define group operations on elliptic curves, and we have also talked a little bit about singular and non-singular elliptic curves.
Yeah, can you finish the second part in 5 minutes?
Yeah, sure. Now we will discuss about the applications of elliptic curves in cryptography. A brief introduction to cryptography. So basically what we do in cryptography is we want to design a crypto system in such a way that designing the crypto system won't be a hard problem, but breaking the crypto system will be a hard problem, as we call it as a trapdoor function. Now there are two types of crypto systems. One is symmetric key crypto system, another is asymmetric key crypto systems. So in symmetric key crypto system, the key that is used for encryption and the key that is used for decryption are the same keys. For asymmetric key or public key crypto systems, the key that is used for encryption is different from the key that is used for decryption. So in symmetric or secret key crypto system, if we make the key public, then there is no use of building the crypto system, and adversary can easily break it because you are using the same key to encrypt and decrypt. However, for public key crypto system, we can make the encryption key public because it won't make a difference. We have a separate private key, sorry, for decrypting the crypto system. So these are some examples of public key crypto systems. The Diffie-Hellman key exchange, which was proposed by Whitfield Diffie and Martin Hellman in 1976. We will discuss about this in later slides because it is involved in elliptic curve cryptography. We have the RSA crypto system, which was proposed by Ron Rifest, Adi Shamir, and Leonard Adleman in 1977. A little bit about RSA. Here we multiply two very big prime numbers to get an even bigger composite number. Now multiplying two prime numbers is not a tough problem, but given the composite number, it is very difficult to prime factorize it back to those very big prime numbers. So that is about the RSA. So it is also a trapdoor function because one way it is easy to compute, but the other way it is difficult. And elliptic curve cryptography, ECC, is an public key cryptography which is done over finite field elliptic curves, and it was proposed in 1985. So here is a little bit about elliptic curve crypto systems and finite fields. So why elliptic curve cryptography is the first question that comes. So elliptic curve cryptography allows smaller keys compared to non-elliptic curve cryptographies. As far as I remember, I think 1024 key size in RSA is equivalent to 160 just in elliptic curve cryptography. I'd have to check it. I'm not very sure about the information, but something like that. In cryptography, so when we are discussing about the group function, we were discussing it over rational numbers. But in cryptography, we use elliptic curves over finite field or Galois field. So what is a finite field? A finite field is a set with a finite number of elements. And in fields, we basically have two binary operations, addition and multiplication. And both of them satisfy the closure associative, existence of identity, and existence of inverse properties for both the operations. For example, integer modulo p is a finite field. How many elements we will have there? We will have p elements from 0 to p minus 1 because we are doing integer modulo p. Okay. Finite fields have a single prime power cardinality, p to the power k, where p is a prime number and k is a positive integer. And you can show that finite fields will have that cardinality. So elliptic curve cryptography was proposed by Neil Koblitz and Victor S. Miller back in 1985. Now we will come to the most important part, that is the elliptic curve discrete logarithm problem. And we will see how we can use it in cryptography. So like we discussed, a trapdoor function which is easy to compute in one way but difficult to break the other way. As the same thing we have in case of discrete logarithm problem for elliptic curve cryptography. So if we know 2 points P and Q such that Q is NP, so P is operated n times to get Q. So if we are given the point P and the point Q, it is very difficult to find out what n is. It is a very hard problem. So if somebody is doing the operation on P n times and finding out Q, for that person, the operation is easy because they know n. But if we are given those 2 points, finding out n is a very difficult problem. That's why it's used in cryptography, because it is again a trapdoor function. Unless and until we know n, we cannot break this crypto system. So this is the elliptic curve discrete logarithm problem. Now we will move to Diffie-Hellman key exchange. So the Diffie-Hellman key exchange is basically a public symmetric key crypto system. Now what we learned in symmetric key was that the key for encryption and decryption are both same. But in Diffie-Hellman key exchange, what's happening is the key exchange is happening over a public channel. Now, what are the problems while exchanging key or through public channels is that if we exchange the key, then the adversaries are getting to know it, right? Because it is over a public channel. So we have to exchange the key in such a way that the adversaries do not get to know the actual key. So we have to be very careful about that. So we will use the discrete log problem here and see how we can exchange keys. So say the key will be exchanged between person A and person B. We can call them Alice and Bob here. Let us understand how we will do that. We saw that given P and Q, where Q is equal to NP, it is a difficult problem to find out N, right? So say there is a generator point G. G is, the P that we discussed in the previous slide. G is another point. We are taking a generator point G. Now the generator point G is made public. The elliptic curve equation is also public, and the finite field is also public. So for a generator G, say Alice is computing it A times. So Alice is calculating AG. A is private to Alice. Alice is not making A public. Similarly, Bob is doing BG. B is private to Bob. Bob is not making it public. What they're making public are AG and BG. So Alice is sending AG to Bob through the public channel, and Bob is sending BG to Alice through the public channel. Note that A and B are still private to them. So now what does Alice have? Let us see what Alice has. Alice has A, Alice has BG, and Alice has AG. And what does Bob have? Bob has B, Bob has AG, and Bob has BG. Now what Alice is doing, Alice is computing A, BG. Alice has BG because Bob gave her BG through the public channel. Alice already has her A. So when Alice is doing A, BG, A into BG, Alice is getting ABG here. And what Bob has, Bob already had B. Bob got AG from Alice. So Bob is doing BAG, which is again ABG. So see at the end, Alice and Bob has the same secret key, and A and B are not made public. So this key will remain public to Alice and Bob because the adversary does not know A and B, and it is very difficult for them to find out A and B because we already saw that in the discrete log problem. So even though they are sharing some information through public channel, the final key is private to both Alice and Bob, and that was our prime objective. And we have done that through Diffie-Hellman key exchange. Finally, we will talk about the impact of quantum computing on classical cryptography. So in 1994, American mathematician Peter Shor. Pardon?
Can you quickly wind up in a minute?
Yeah. It will be done in a minute. So in 1994, American mathematician Peter Shor did a groundbreaking research. His algorithm, the Shor's algorithm, can be executed on quantum computers, which will extract the prime factors of an integer. That is, it will break the RSA crypto system, and it will also solve the discrete log problem efficiently. That is, it will also break the elliptic curve crypto system. And that's why, according to the National Security Agency, NSA, they gave out a statement that for those partners and vendors that have not yet made the transition to SUD B algorithms, elliptic curve cryptography, we recommend not making a significant expenditure to do so at this point, but instead to prepare for the upcoming quantum resistant algorithm transition. Because in post-quantum era, the elliptic curve cryptography can be easily broken using Shor's algorithm. So it is advisable to move to post-quantum crypto systems or crypto systems which cannot by quantum. So that is the end of my presentation. If you have any questions, you can ask me.
Okay, thank you so much for the wonderful talk. So if there are no questions, then let's proceed to the next talk.
Excuse me. Hello.
Yeah.
Yeah,
Hello.
I have a doubt. Shubham this side.
Yeah. Hi.
Small doubt. Yes. Hi, Sona Jodi. First of all, thanks for this nice presentation. Just a small doubt, like when in that key exchange, when Bob and Alice were sharing AG and BG.
Hmm.
So on the public channel, which advisory can still see. So he has AG and BG. With these two information, can't he predict ABG?
No, no, because for calculating ABG, okay, now let's say that the adversary has BG, right? Now we need
Hmm.
to calculate ABG. Okay,
Hmm.
now finding out A is a hard problem as we discussed in discrete log problem, right? Because Alice is doing AP equal to Q. Okay,
Hmm.
so
Hmm.
given P and Q, finding out A is a hard problem. So even though
Hmm.
the adversary has BG and AG, they can't find out ABG, right? They can find out AGBG, but that won't do any good.
Got it. Okay. Thank you.
Thank you. Okay, so I think
Thank you, Sunadhuri. Um, we'll start off with the next talk by Raj Kumar. Raj Kumar, are you here?
Yes, ma'am, I'm here, ma'am.
Yeah,
Shall I share my writing pad?
sure. So Rajkumar is going to talk on trigonometric ratios. So please introduce yourself and then you can start.
Okay, ma'am.
So you can take up to like at most 1 o'clock, including discussion. So please stick to the timing.
Yes, ma'am, my own small thing that in sharing system, it is not showing the writing pad, ma'am, while sharing my screen.
Now, have you connected your writing pad
Yes,
and
ma'am. It's connected, ma'am.
yeah. So what are you writing on? Means you would have opened some PDF or something to write on, right?
No, ma'am, just since it is a basics about trigonometry, I'm focusing on the basics and little bit it will be coming to the moderate level. So that
That is fine. That is fine. But you will be writing on something, right? Like
yes,
in the
ma'am,
sense you
writing
will
pad
open a
only.
PDF and write an empty PDF or something, right?
Yes, ma'am.
So you should choose that, right?
So,
Share and then
if I'm clicking on share, ma'am, it is coming allow WebEx to share your content. Then open system preferences. If I'm clicking on it, means it's not showing anything, ma'am.
now have you opened a tab or something like um, so what application are you using to write it on? Means what is the app that you're using to write? You'll connect the writing pad and then write on what?
In PDF, ma'am. Like
So
a
have you opened that PDF?
yes, ma'am, open, ma'am.
Then you should get the option, right? When you select share.
Now start new to new whiteboard. I got it, ma'am.
Fine. You can share and then you can start. We'll wind up yours by 1 so that we can.
Okay, ma'am.
Yeah.
The comments are 1 minute, ma'am. It's coming, creating a new whiteboard. Wait a minute.
Yeah. We can see your whiteboard.
Yes, ma'am.
Okay.
It's going on somewhere. Excuse me. Just adjust with me because my hope it is visible, ma'am. Hello.
You can go ahead.
Okay. Hello, I'm Raj Kumar. I'm from Tenkasi. I'm doing my IIT data science degree, second semester. Now I'm going to present about the basics of trigonometry, all of you know. So little by little, step by step, we'll build up to the moderate and build it to the higher level. So I'm going to present with my trigonometric basics. So we all know about the trigonometric identities. So let us start with that. So trigonometric identities in the sense we all know sine square theta plus cos square theta is equal to 1 and secant square theta minus tan square theta is equal to 1 and cosecant square theta minus cot square theta is equal to 1. So these are the fundamental basics you might have been studying from 9th to 12th. And apart from that, I'll also share with you the Pythagoras theorem. So Pythagoras theorem, you all know.
Rajkumar, sorry, can I interrupt you?
Pythagoras theorem, sir.
Yeah, no. I'm just asking. Can you please change your pen mark, the logo marker, which is somewhat away from the where you are writing?
Okay, but here it is fully visible. Okay, is this okay, sir? It is very thin.
No, the icon or pencil icon.
Yes, sir. 1 minute.
Yeah. Change it to somewhat else.
Mm. Is this okay, sir?
Yeah, it's okay.
Okay. So we all know that. So this is an angle. The theta means so opposite to that. This is the opposite side. So opposite to the angle theta is the opposite side, and this is the adjacent side. So I'm writing short, and hypotenuse. The longer side is the hypotenuse. So from this we know. So AC square is equal to AB square plus BC square. That is, in other words, we can say hypotenuse square is equal to opposite side square plus adjacent side square. Now we learn about the identities. It inverse. So inverse of trigonometric identities. Inverse of trigonometric. So the inverse of sine theta is, excuse me. So inverse of sine theta is equal to, that is 1 by inverse, that is inverse we are writing, since 1 by sine theta is equal to cosecant theta. Similarly, inverse of cos theta is equal to secant theta, and inverse of tan theta is equal to cot theta. So these are the things. Now we'll hope it is clear. And next I'll change my slide. Ma'am, shall I change it, ma'am? Shall I go to the next slide? Is the whiteboard visible, ma'am?
Yes, it is visible.
Okay, now I'll excuse me. Okay. Now came to the next slide. Now we'll talk about the trigonometry angles, because step by step from the scratch only we can build the trigonometry concepts. So now trigonometric angles. So these are the trigonometric angles we found out. Now we will
Sorry,
start from
sorry,
0.
Rajkumar.
These are,
We
these are the
cannot
Ah,
see what you are writing on the whiteboard.
okay.
I think you have not changed the slide.
Now sorry, sir. Now I can change it to the little thickness, minimum thickness level. So the trigonometric angles we have learned from our 9th and 10th, and till 90 degrees we have learned. Then after that to the higher level it will be going on. So we'll discuss about that from the scratch. Is it okay now, sir? So 0.
Able to see what you have written below trigonometric angles. That's the last thing we are able to see.
Now from starting from 0 I wrote, ma'am.
No, we are not able to see that.
But sir is telling to change the pen. So it okay. Is it okay now? 0.
No, we are still able to see your previous screen, the previous trigonometric ratio and all.
Okay.
Not the new one. Whatever stuff you are writing, not able to see that.
Now is it okay, sir?
No, we are still means only the first screen is trigonometric ratios, inverse of trigonometric identities. Only those are visible. Trigonometric angles, whatever you've written below trigonometric angles is not visible. Yeah, now you're erasing this.
Yes, ma'am. Trigonometry angles that is visible, ma'am.
Are you not able to open a new pad, a new whiteboard?
New page or something, the next page was
Yes.
this.
Actually, I am able to scroll down, sir. This is the scrolling option is there in the whiteboard. This is the previous content what I wrote. If I'm scrolling down means it is coming as a blank page.
Yeah, but
So
we are not able to see that.
now it is blank. Are you able to see? Now I'll write and show you, ma'am.
No, now we are still seeing the ratios page.
Okay, then shall I erase and write, ma'am?
Yeah, that will be better.
Okay, ma'am.
Can you quickly wind up? We'll close by 1.
Hereafter only the important content is going to come, ma'am. Okay. Just
But erasing will consume your limited time.
Sorry for that, sir. Just a minute.
To open a new, I don't know how
You can just close this and open a new one. That will be better.
Okay, ma'am. Okay. Now, now is it okay, ma'am? Trigonometric angles.
Yeah. Please wind up in another 10 minutes.
Sure, ma'am. So we all know we have studied that before going to the trigonometric, I'll just recollect the formula. Sine theta is equal to opposite side by hypotenuse. So sine theta is equal to opposite by hypotenuse, and cos theta is equal to adjacent side by hypotenuse. Then tan theta is equal to opposite by adjacent side. Now, we'll know about constructing the angles. So we all know there are different types of angles. So it is 0, starting from 0, 30, 45, 60, and 90. So these are the things we studied from 9th and 10th basically. So all of us will be by hearting this with sine 0 is 0, sine 30, the value of sine 30 is 1 by 2, and sine 45 is 1 by root 2, and sine 60 is root 3 by 2, and sine 90 is 1. Then here is lies the trick where, so the start here we saw for 0 to 90 sine 0 to 90 from 0 till 1. So from 0 till 1 straight it is going. So for the cos theta, you just reverse the direction. So for cos 90, it is coming 1, then reverse it, root 3 by 2, then 1 by root 2, the same value coming again for cos 45, and cos 60 is again 1 by 2, so reverse it and 0. Now whenever we are coming to tan, we know tan theta is equal to sin theta by cos theta. So 0 divided by 1. So you divide the 0 by 1. So any number that is dividing the 0 in the numerator and 1 in the denominator, it becomes 0. And 1 by 2 and root 3 by 2, you make the inverse, it will become 1 by root 3. And 1 by root 2 and 1 by root 2, so both the tan, it becomes 1. And tan 60 root 3 by 2, so I'll write here as a sample and show. So root 3 by 2 into 2 by 1. So if it goes up, then 2 and 2 will get cancelled. Then the balance is root 3. Then tan 90 1 by 0. So anything divided by 0, it becomes infinity or not defined. So these are the basics. Now we'll go to the higher angles. So from here, we'll construct for the higher angles. So 0. Again, so 0 and 90 I'll write because already the in between the mean 30, 45 and 60 we all know. So from 0, 90, 180, 270 and 360. Now here comes the higher difficulty level. For this superb shortcut trick is there. So basically the method is the simple pendulum method. So you should construct a pendulum like this. I'm writing on the top corner, top left corner. So you write the values as -1, 0, 1. Hope this area is clear. Okay, so I wrote on the top. Now I will again start with the sine theta, cos theta, then tan theta. So in the radian format, I'll write, so sine 0 for the radian 0, then 90 is pi by 2, then 180 is pi, and 270 is pi plus pi by 2. So every 90-degree angle it is getting added. So therefore 3 pi by 2, then 360 is 2 pi, 2 into 180. So pi stands for 180. So therefore 2 into 180, it stands for 360. So now let us look for sine theta. Okay, so sine 0, we already know sine 0 is 0. So what is sine 90? It is 1. Now we'll go to the simple pendulum. So where the top left corner where I wrote. So from 1 we should start. Okay, so 0, sine 0 is 0, we already know, and sine 90 is 1, we already know. So from there, okay, from 0, 1. So I'll just take it. So look very carefully, 0, 1. Then it comes back to again what value? It is 0. So therefore sine 180 is also 0. Okay, then backwards it is little bit going backward. So like a simple pendulum format we have constructed. So it comes to again -1. So therefore sine 270 is -1. Then again it will come to 0. So therefore sine 360 is 0. Got it all of you? Now cos 0. Cos 0, it is just a reverse. Cos 0 is 1. So what is sine 0? Sorry, cos 0 is 1. Cos 90 is 0. So therefore we should start from 0. I'll just I'll just rub it here and explain it one more time for the cos values. So these are the areas where our students will struggle usually. So -1, 0, 1. So therefore, we are starting from 1. So look at the cost table. So from 1, then 0. Okay. So from 1, 0 it is going on here. So next what value will come from 1 to 0, then 0 to -1. Then from -1 to 0 again. So therefore, it becomes 0. So after 0, it is 1. Therefore, it becomes 1. So tan we already know, sin theta by cos theta, that is tan theta. So 0 divided by 1. What is 0 divided by 1? 0 divided by 1 is 0. 1 divided by 0, that is tan 90, that is infinity. Anything divided by 0 is not defined, infinity. Okay, so therefore 0 divided by -1, again 0 here. Then -1 by 0, again infinity. So 0 divided by 1, 0. So like this, we should find the values. I hope all of you got it. Now next, we'll go to the trigonometric angles, how we should find the larger angles with the trigonometric signs like sin theta and cos theta. So I'll go to the next page.
Rajkumar, is there a problem?
No, ma'am.
Oh.
Just a minute.
Yeah. How long will you take?
Oh, just 5 seconds, ma'am. I'm closing the whiteboard and starting new.
No, no. How long will you take to finish the talk?
5 minutes, ma'am.
Yeah, okay.
Now I'll say about the angles. That is quadrants. So which quadrant will be coming? So now I'll draw a circular object. This circle I am dividing into 4 quadrants. And here also. So this is the first quadrant, this is the second quadrant, this is the third quadrant, and this is the fourth quadrant. So in the first quadrant, all signs are positive, all are positive. The sine, cos, tan, everything is positive. Here, only sine and its inverse is positive. Therefore, only sine. So its inverse is cosecant. So sine and cosecant are positive. That is, since it is all, so in short form, A will be representing. Since only sine is positive, we are writing it as S. Then here in the third quadrant, tangent and its inverse. So I'll writing in the bottom. Tangent and its inverse is cot. So both only tan and cot are positive. And here only cos and secant are positive in the fourth quadrant. So in the short form, since in the third quadrant tan is positive, we are writing as T. And here in the fourth quadrant, cos is positive, we are writing it as C. So ASTC. So A, S, T, and C. So we can denote it as all silver tea cups. If you like coffee means you can think it as all students take coffee. So these are the angles we should keep in mind because these angles will be helping us in the short form to crack the competitive examinations too. Now, the first quadrant we saw all are positive. In the second quadrant we saw only sine and its inverse cosecant are positive. In the third quadrant tangent and its inverse cotangent, that is cot, it is positive. And in the fourth quadrant cos and its inverse secant is positive. Now let us see. Now let us see about the core ratios. So inverse is trigonometric ratios. We are coming into it now, that is co-ratios. So inverse are extremely different from co-ratios. Let us see about that now. So the co-ratio of sine theta. Co-ratio of sine theta is what? It is cos theta. So similarly, co-ratio of cos theta, it is inverse, okay, sine theta. So keep that in mind. Now, similarly, co-ratio of tan theta is cot theta. And co-ratio of secant theta is cosecant theta. Okay, now we'll go to the topic. Now I want to find the bigger angle. Now we saw about the sine 180, 270, 360, everything. In the radians also pi 2 by we saw 3 pi by 2 also. Now in between the mean angles they are asking. So like this sine 150. What is sine 150? They are asking. So in the terms of 90 degree, you should split and write this 150. How I'll show you. So sine. So in the place of 150, what you should do is sine 90. Okay, into one number. So into one number, sine 90, that is into 1. Okay. So what is the remaining? Already out of 150, 90 we wrote. So the balance number is 60. So sine 90 into 1 plus 60. So therefore, one very important trick is there. First, we should see which quadrant. So as a short form at the corner, I'll write here. First, we should check it, which quadrant it is lying. Whether it is the first, second, third, or fourth. So quadrant we should check. And secondly, we should check the co-ratio. So quadrant and co-ratio. So first, sine is lying in the which quadrant? Sine, here it is lying in the second quadrant. Therefore, here we need to find sine 150. Yes, it is positive. So the angles which are in the anti-clockwise direction, they are taken as positive. And the angles which are in the clockwise direction, they are taken as negative. Since we are taking in the anti-clockwise direction and sine lies, it is in the same place. So we can write it as sine. There is no problem about that. Okay, but we should see the 1. Sine 90 into 1. If it is the odd number means you should change the co-ratio. What is the co-ratio of sine? So odd is other co-ratio. Okay, odd number means co-ratio and even number means same ratio. Just keep that in mind. So we have come to the conclusion of our session. Just a minute. Okay. So sine 90 into 1. Sine 90 into 1. First we saw whether sine is located in the quadrant where it falls. Yes. Yes, sine is, it is in the first quadrant. That is second quadrant. All silver teacups, second quadrant. So that is not a problem. But here if you are seeing, it is 90 into 1. 1 is the odd number. So therefore, we should write the co-ratio of sine. So what is the co-ratio of sine? That is cos. Okay. So cos. Sine is positive or not, we should check. Yes, it is positive because it is lying in the second quadrant. Because sine 90. So if I'm starting from 0 till 90 degree. 90 plus theta. So that theta, that 60 degree, it will be coming in this direction. So therefore, the 60 degree lies between, that is balance sine 150. 90 plus 60 is 150. Sine 90 plus 60. That 60 lies in the second quadrant. Since it is lying in the same quadrant, it is positive. That is not a problem. But since it is an odd number, we are changing the co-ratio as cos, then writing the number after the addition sign. So therefore, cos 60 we are writing. Therefore, cos 60 we all know, that is 1 by 2. Sine 30 is equal to cos 60. That is 1 by 2. Now another one sum we'll see. Now another one is tan 350.
110.
Yes.
Can you quickly finish this?
Yes, I'm going to finish. This is the last sum. So tan 315 means in terms of 90 degrees, we should write. So the nearby number 90 multiplied by a particular number. So 90 into 1 is 90. 90 into 2 is 180. 90 into 3 is 270. 270 plus one number, one angle will be giving us 315. So I'm writing 90 into 3 plus 45. So 90 into 3 is our 270 plus 45. So it is 315. So therefore, we should check tan is positive or negative. So tan here we will see. So tan is lying in the third quadrant. But here 315 it is coming. So therefore 0, 90, 180, 270 on the line. 270 on the line. Then 315 plus 9, that is 270 plus 45. Therefore, in the fourth quadrant it is coming 315. Since it is cos, only tan is positive in the third quadrant. Since it is lying in the fourth quadrant, therefore we take it as negative. So first step over. Next, we are checking whether it is a odd number or an even number. It is a odd number. Therefore, we should write the co-ratio of tan. What is the co-ratio of tan? Cot. So therefore, you just write it as minus cot. And the remaining angle 45, you write it. So therefore, 45 is equal to cot 45. Tan 45 we know 1. So its reciprocal also 1. Since minus sign is there, we write it as minus 1. Thank you. So we have come to the end of the session, and I thank Abhijit sir and Sushmita ma'am for granting me this opportunity. Thank you so much. And so from the scratch, if you are building like the higher order concept means very difficult concept means it will be easy to understand for all the mathematics as well as stat students. And thank you for giving me the opportunities, dear tech team. Thank you.
Thank you so much, Rajkumar. So we'll, are there any questions? Okay. Anyway, since we are running short of time, we'll close the session and we'll meet at 2 o'clock after lunch and we'll continue with the other remaining talks. And at
Thank you so much.
4 o'clock, there's this prize distribution ceremony. So we'll meet at 2 for the talks. Okay. So we'll break for lunch now and meet at 2.
Hello.
Good afternoon, all. I hope you guys had lunch. So let's begin the afternoon session quickly. Since we are running out of schedule, means we were supposed to have 5 talks in the morning and 5 talks in the afternoon, but since we were a little delayed, we'll have 6 now. So we'll start off with Deepak's talk. So Deepak will be presenting on mathematics and its deeper philosophy, right?
Yeah.
Yeah. So you can introduce yourself and then go ahead.
Yeah.
Can you share?
Yeah, you can use the mouse. It's not touch. Shit.
Yeah.
And then full screen.
From where? Is this one?
Yeah, this one from beginning.
Okay. Let's start. Uh, Good afternoon, everyone. So this is Deepak Pandey, and I'm the core member of the Math Stats Academic Cell. And I think this is the biggest opportunity I got, the platform I got to, explain my things, add some innovation, and even try my best to give some more greater and bigger ideas regarding maths and statistics. Because I think, what I really think, from past many years, like from 100 or 200 years, the most important part which we have seen is the development of maths, development of science. Okay. And this mathematics and statistics academic cell is going to be, it can have a bigger and a brighter future regarding this. So this is Deepak Pandey, and I'm doing engineering also from the electronics and communication. So the topic of my the topic of my discussion is mathematics with the deeper philosophy. I think we all know what is the philosophy. If you don't know, let's come to the point. Okay. So coming to the point, let's talk about philosophy. Philosophy is a very interesting subject because it adds up the imagination. The study of general and the fundamental questions such as those about existence, reasons, knowledge, values, mind, and language. But today, what I really want to discuss is about the imagination. And when I talk about the imagination, there is a part which we call creativity. And with the creativity, the important thing which comes out is mathematics. So, as we know that philosophy, Newton's, Einstein's, and many other scientists, they were the part of a philosophy. They used the mathematics, but they were the part of a philosophy. Like Newton's articulated a broadly implicit philosophy of science, explicitly in his rules of reasoning in philosophy at the beginning of book 3 of the third edition of the Principles, and implicitly in his derivations of the inverse square law from astronomical data. So, like coming to the mathematical philosophy, the first thing I want to tell you is a language which accurately can be considered to be the something which is not simple to understand. Mathematics is a totally different tool which can be applied on the science, which can be applied on the physics, chemistry, or even biology, and we can create a bigger innovation from that. So on the one hand, the philosophy of mathematics, let me tell you, on the one hand, the philosophy of the mathematics is concerned with the problem that are closely related to the central problem of the metaphysics. Let me tell you, this metaphysics, this is a very good term. Metaphysics, when we talk about the mathematical philosophy, the metaphysics is the most important part, because the metaphysics, which is actually which is something which is related to the innovation and the imagination. I'm coming to the metaphysics. Yeah, and epistemology. It is also a very important topic which comes under the mathematical philosophy. At first blush, mathematics appears to study abstract entities. This makes one wonder that the nature of mathematical entities consist in and how we can have knowledge of mathematical entities. If these problems are regarded as intractable, then one might try to see if mathematical objects can somehow belong to one concrete world after all. No, so this is something I want, let you, I just want you to think about it once, that how it can be very much related to the physics, how much it can be very much related to the chemistry. Okay, so coming to the next point. Yeah, so let's talk about the philosophy which Einstein look, the philosophy which Isaac Newton look. Okay, so when we talk about the Isaac Newton's philosophy of mathematics, it says that applying his philosophy, the principles of philosophy, Newton discovered the mathematical form of the gravitational force between the two bodies is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. I think we all know the gravitational law. It's always like gravitational law. Wait a minute. Gravitational law which deals with the masses and the inversely proportional to the distance. When Newton was thinking about this mathematical calculation, it was not the first thing which he thought. Okay, he thought he has some imagination. He thought about the imagination. He thought about how the things can come down. Okay, then he started calculating this can be related to the maths or not. And then he started understanding the maths. He used the tool as a maths and started describing the nature. So the same way the philosophy also deals with the imagination. When you imagine something, you start thinking more deeper about it. You think in a creative way, and when the creative sides come under, it uses the maths. And the Newton used the mathematics to prove his own imagination, his own thinking. And that's why the gravitational law, where he just anyhow he calculated that the gravitational force is directly proportional to the two masses and inversely proportional to the distance. So that is something he tried to think of with a creative order. Okay, let's talk about one more greatest scientist, Albert Einstein. He was one of the most god-gifted talent with a a very high understanding of physics, high understanding of how to understand the nature in more different way. So he just given the theory of relativity, one of the most famous equation till now, which says E equals to mc square. I know, I think we all know this. I think we all read it from our class. Like the energy is directly proportional to the mass and multiplication of the square of the speed of the light. Okay, so this is something we all know. Okay, but he also used the imagination. He also think about some deeper aspects of the physics. Maybe he thought about the gravitational force, how it works, how the things can be formulated in some way. So then he just there's some like in his theory he just discuss about the time dilation. Let me discuss about time dilation. It is also one of the part of the philosophical, the aspects of philosophy. When we think about philosophy, we think about the Einstein's imagination about the science. So it talks about t t t equals to t naught upon under root 1 minus v square upon c square. This is the time dilation. Let me tell you how this come, like how it come into the picture. Uh, Inertial frame and a non-inertial frame. Okay, when I look something from an inertial frame, the things are in a more different, like there is some difference between the inertial and the non-inertial frame. Okay, when we observe something in non-inertial frame, there is some time dilation which comes under the under the consideration, and that is only the difference in the time. This t naught was the actual time from the main difference, the actual difference, the frame of reference. But when we go to some different time zone, or like in a different frame of reference, there is slightly the change in the t, and that only Einstein proved. Einstein just showed this, that when we change the frame of reference, there is some change in the time. Okay, so I just want to clarify one thing. Even he used the philosophical aspect of understanding this nature. Okay, he observed the things in a more deeper manner, in a more creative manner, and that's how he got the result like this. I think I'm not going to go more deeper about the theory of relativity or some more complex theories, but what I actually want to tell you, that philosophy has always been the part of a science. It always comes under consideration whenever we talk about creativity, imagination, and every innovation which is coming under the consideration. There are many different angles of philosophy, but right now I only want to focus about one angle, and that is the philosophy in science, the philosophy in mathematics. Okay, so let's come to the next slide. Yeah, here we can say that this time is the time observed in the other reference frame. Okay, and t naught time in observed from the own frame of reference, the frame of reference where which is fixed. Okay, and v is the speed of the moving object. Yeah, there is a moving object in that non-inertial frame, and that is the speed of that particle, and the c the speed of light. Okay, so I think it, like, there's no problem in this. Like, there is some change in time which comes under the consideration when the frame of reference changes. So that is something he thought of, he imagined of, and he proved it through the mathematics. Mathematics was the tool to prove that, and the imagination comes under his philosophy. Imagination comes under his own imagination. That I really believe. Okay, so let's come to the next slide, which talks about, there are three schools of philosophy. There are three schools of philosophy. Logic, like, it's just based on the logic, the formalism, and there's one more, intuitionism. It is also a very important part of defining the schools of philosophy. Okay, so let's start studying about the first school of philosophy, the logicism. Okay, when we talk about the logic, when we think about the logic, we feel that what can be the way, wait a minute, when we think about logic, we talk about how the things can be done in a logical, in a in a certain way. The logistic project consists in attempting to reduce mathematics to logic. Okay, since logic is supposed to be neutral about matters ontological, there's one scientist, Fridge, a person. Wait a minute. Yeah, so I was talking about the logicism. Yeah. So there's one scientist known as Frege. He devoted much of his career to trying to show out how mathematical can be reduced to the logic. Okay. Like he just wanted to claim, he wanted to prove that how the mathematics can be converted to the logic. Okay. And let me tell you one thing. In philosophy, the logic is the most important part. After the metaphysics, after after some more good topics, the logic is the most important part of the philosophy, and this logic is the most important part in even mathematics. So the Frege devoted much of his career to trying to show how mathematics can be reduced to logic. He managed to derive the principles. There are some arithmetic principles, some equations which he tried to show. He just wanted to prove that how the logic can be added to the maths. And I think logic is the most important part. This is the equation. This is the equation, a most famous equation of his time, which directly claim that the logic is the most important part of proving whole mathematics. Logic which really focuses that how the formulas can be discovered, how the formulas can be formed, and how the formulas can be run for the different things, even for the black holes, even for the singularity, even for the different cosmosic like cosmos things or different things. Even the quantum physics uses the logic. So that's the important part, I guess. So the next thing is, yeah, like this is the most important topic. This is the most important topic because according to this, mathematics is essentially an activity of construction. This part of philosophy deals with the construction. Let me define how it deals with the construction. The natural numbers are mental constructions. The real numbers are the mental constructions. Proofs and theorems are the mental constructions. This is something which deals with the construction through the natural numbers, the real numbers, through the proofs, through the theorems. I think I'm like right now I'm not proving any big equations because this is something I really want to tell you, that philosophy is very much related to mathematics in terms of mental construction, proofs, and theorem. Yeah. So mathematical meaning is a mental construction. Mathematical constructions are produced by the ideal mathematics. Abstractions is made from the the physical limitations of the real life. But even the ideal mathematicians remains a finite being. She can never complete the infinite constructions, even though she can complete arbitrary large finite initial parts of it. This is something the most important thing which one has to focus on, because it just want to it has some limits. It just only want to be in some limits. It don't want to cross some limits. For example, like let me tell you, key this entails that this resultant rejection the existence of the actual infinite. Only potentially infinite collections are given in the activity of construction. It don't deals with any infinity. It just want to have the limit. It just don't want to get to see some what the magics are shown in the infinity, what the things come under the infinity. It just don't want to deal about it. It just want to restrict itself. It just says that a basic example is a successive construction in the time of individual natural numbers. So from these general consideration about the nature of mathematics based on the conditions of human mind, the non-constructive existence proofs are the proofs that purports to demonstrate the existence of a mathematical entity having a certain property without even implicitly containing a method of generating an example of such entity. So that is something, this point, the non-constructive existence proofs are the proofs that purports to demonstrate the existence of a mathematical entity having a certain property without even implicitly containing a method of generating example of such an entity. That's a very important part of this like this whole process. Let me come to the next point, that is formalism. Okay. The formalism is also a very important topic, which deals with the formalizing the things, deals with creating more formulas. about the bigger aspects. Okay, when we talk about black hole is one of the part of the formalism. This is something, the use of formalism, it actually has to formalize everything in some certain order to give some like important outputs. So that is the use of formalism. So this is the last thing, the future with the mathematical philosophy. I think philosophy is something which is never going to end. Okay, it's always going to be there. When it comes about the mathematics, it only deals with the creativity, it only deals with the imagination, and thinking more about cosmos in a creative manner, formalizing the things, and giving some more better outputs. So that is all about the deeper sense of philosophy in mathematics. So this is all about the philosophy with the mathematics. If you really want to like have interest anymore, like I can share this, my own research paper in this. Like I have some research paper regarding that. You can read about it. And thank you for that. Yeah, thank you. Yeah.
Thank you, Deepak. So if you have any questions, you can write to Deepak. Yes, your email ID. Yeah, I'll just put it on chat in case there's any questions, they can write to you. Yeah, and so thank you, Deepak. So let's have the next speaker, Kalyani. Kalyani, are you there?
Yes, ma'am.
Yeah. So, Kalyani, you have 15 minutes to present. So, Kalyani is going to speak on mathematics behind NLP, vector semantics. So, Kalyani, please, you can start and you can take 15 minutes. Please introduce yourself and then go ahead.
Sure. Please sharing my screen. So my screen is visible.
Yes, yes.
Yeah. So hello everyone and welcome to this workshop on mathematics and statistics. So this is Kalyani from BS degree. We will be having a today's talk on this mathematics behind NLP. So how mathematics is used in a natural language processing. So I'm starting with the NLP and how do we use mathematics in that. So Google, okay Google, Alexa, hey Siri. So these are the day-to-day applications that are all are using NLP. So the okay Google launched the WhatsApp. Hey Siri, please call my mom, and hey Alexa, please play my favorite song. So all these all are the aspects that you are using day-to-day NLP aspects we are using day-to-day our life. So what is the main goal of NLP as such? So what for this research of NLP is, so if you think about it, there is a very broad scientific goal of this field, NLP. So it can be understand language. Can we have a deep understanding on how human process language? So can we teach computers how to understand language? So how computers understand language and they can may respond with the human like the way human can do. This is the very longest aim of NLP. So NLP tells us how do we pre-process the data and how do we pre-process the language? How do we deal with this language morphology and language syntax? So in today's talk, we will be going to some advanced topics in NLP, that is semantics. So we are talking about semantics and how do we capture semantics. So As such, when I say semantics, so when a semantics word comes to your mind, in general, basically syntax talks about the arrangement, how the different words are arranged and the language in while we talk about the semantics, it immediately move from arrangement to some sort of understanding, some sort of meaning domain. So I want to find out what is the meaning of different words, how they do combine together to form a meaningful sense. So, to form a meaningful sentence and can be a large text, the document, it can be a very big, huge content. So, if I like to give the definition of the semantics, basically semantics is used to identify the meanings behind the words. So I can say that it is the study of meaning. That is what is the relation between the symbols and what they do. They denote what exactly the meaning of the word they denote. So we are trying to find out, yeah, NLP is how to, we are just using this natural language processing. Computers can understand the language. So we are trying to deal with the computational semantics. So we are trying to find out how in general computers can produce such a semantic representation. Like what is a computational semantics? Basically, it is a study of how to automate the process of constructing and reasoning with the meaning of representation of a natural language expressions. So basically, these computational semantics are divided. Methods are can be divided into the two major categories. One is the formal semantics, and another is the distributional semantics. So in a formal semantics, which is a construction of a precise mathematical models of the relation between expression in a natural language and the world. While in a distributional semantics, it is a study of statistical patterns of how human word uses to extract semantics. So when we talk about these methods, these are the two different methods. One is based on formal semantics and another is based on distributional semantics. So basically it tells that what is the relation between various expression in the language and also relate them to whatever there is and there in the world, like whatever the word represent, that exactly they express. So the next is a vector semantics. So this is a dimensional space of the vectors. Vectors as a word. These words are represented as a vectors. So what is a vector semantics and how vectors are used in a semantics? So that thing we are going to see now. So basically, vector semantics is the standard way to represent the word meaning in NLP. So, helping us many of the aspects of the word meaning to define the meaning of a word, its a distribution in a language, meaning its neighborhood word. So, when we are reading the big context, so if sometimes what happens, some words we are not aware of some words, so we read the full paragraph and just try to infer the context of the paragraph and just try to analyze the unknown word, what they says about it. So the same thing we are implementing in the machines as well. So what we are doing, we are just capturing the neighborhood and their grammatical environments. So their idea was that two words that occur in a very similar distributions, whose neighboring words are similar, have similar meanings. Suppose you can say that here in a green words they are saying very good, amazing, terrific, nice, incredibly good, fantastic. So these are the positive words of the which relates to good. So these are kind of similar words. And here the not good, dislike, bad, worst, incredibly bad. So these are similar with the bad, not good, like that. So they are just similar, just the close to each other in a vector space. So now let us take an example of this vector semantics. So this is the four, I'm just taking the data of the four different sentences. And just we'll see about how do we start constructing this vector or a word space model, and try to see can we see the similarity between the words and how much they are similar to each other. So these are the things we are going to analyze it. So this is our corpus, and this blue data is called as a correlation matrix. Suppose the first word is a cherry. So cherry, we are just identifying the cherry, in which word cherry is neighboring word. Pie and sugar, these two words are more close to cherry. So we can see that maximum words occur pie and sugar with the cherry. The similar with the strawberry, and in the digital and information, these two are computer related words. So we can say that in the context of computer data and result, the more in neighboring words are digital and information. So so these are the four different sentences I given, and I just have to build the vector space model on distributional semantic processing. So how to build the model? How to build the model? How to build the model? I need to start with what the words I want to represent, and these are my target word. So basically these four are my target words: the cherry, strawberry, digital, and information. And those are the correlation matrix. This is the neighboring words which is closely related to 0 neighbor, 1 neighbor, 2 neighbor, and up to 4 neighbor. So based on this data, I am just plotting it on a dimensional space like this. So on a x-axis I have a data, and y-axis I have a computer. So based on that data and computer, I'm just representing the word information. So my information data with the information data is the value is 1683 and the 1670. So I'm just plotting on the plane 1683 and 1670. And for the information thing, I have a 3325 and 3982. So I'm just plotting these two vectors on a plane. These two vectors are like this. So I just point these are known as a word vector. So word vector are represent as a vector of the specific word. So basically the idea of vector semantics is to represent the word at a point in a vector that is derived from the distributional of the word neighbors. And the vectors for representing words are called as the embeddings. Now, just a simple method would be, once you define the context window, you know what are the target words and what your context words. So you are defining the distribution of the target words. Find out how often the words comes with the context word, like window 2 times, 3 times, 0 times, and so on, to define the vectors for different target words. So if we then take every occurrence of each word and its data, suppose I say strawberry. So strawberry and count the context word around it. So we get the word co-occurrence. That is the word to word co-occurrence matrix. This is word to word co-occurrence matrix. Then those two words cherry and strawberry are more similar to each other. Like we can say both pie and sugar tends to occur in their window. Like pie and sugar tends to occur in the same window for cherry and strawberry. So we can infer that cherry and strawberry are more similar words. Similar with the digital and information. Like digital and information are more similar to each other uh, uh, as computer data and results are have the more similar data for the digital and information world. So now this is my the representation of target variables on the vectors as a part of vectors on this plane. Then now we have some intuitions. Let's move on how to examine how much these two words are similar to each other. Okay, so we are going to identify the similarity between these two words. To measure the similarity between these two words, we are using the cosine similarity ratio. So to measure the similarity between the two target vectors, like the vectors is u comma v, u comma w. So this is the cosine similarity formula. Suppose we take the example like cherry and information. Cherry as a vector v and information as a vector w. So I am calculating it. Cosine of the vector cherry and information can be calculated of. We can simply take a dot product of vector cherry with the dot product of vector information and divides by its magnitude. So we can our value is 0.18. So they are not very much similar to each other. Cherry and information. So while digital and information, we take the cross dot product of digital and information. Like this is a digital. These are the vectors. These are known as a row vectors. So we while calculating this cosine similarity, this complete row we are taking it as a row vector. So these two vector dot product of these two vector and divide by its magnitude. That will be give is the similarity ratio. So the cause of digital and information. So the dot product of this vector divided by its magnitude, it comes to around 0.996, which is almost equivalent to 1. So this is most similar words to each other, digital and information. So we can infer that any two different words, we can find out the similarity between these two different words using the cosine similarity, the mathematical concepts. After that, this is a mathematical calculation behind the cosine similarity. So now we are going to represent it as a form of vector. So we can see that see, cosine angle is the angle between the two different vector, like the defined as a cherry vector and the digital vector. The angle between these two vectors is known as cos of these two angles, like cos theta. So this is the vector representation of this data. So the angle between digital and information is very small. Like so, they are more closer to each other. They are more similar. These two words are more similar. And the angle between the cherry and digital is very large. So we can say that cherry and digital are not very much similar to each other. So this is the rough graphical demonstration of cosine similarity, showing vectors of three words like cherry, digital and information. So in the two-dimensional space defined by counts of the words, computer and this nearby. The figure basically, it does not show basically the cosine of this angle, but it shows how these two words are similar to each other. Smaller the angle between the words, greater the similarity. Similarity is maximum. The bigger the angle, the similarity, there is no similarity. That is it. So this is the thing, and the next thing is, yeah, these are the some observation which can infer like cos theta is between -1 to 1. So when we say cos theta is -1, then these two words are antonyms of each other. Okay, and this cos theta is similar to 1, cos of cosine value is close to 1, then that means these two words are synonyms of each other. They are more similar, they can similar words, we can say that. And the next is when theta is 90 degree, these two vectors are perpendicular to each other. That means your cos 90 is 0. It tends to this, the words are not related. These are unrelated words. They don't have a similarity. They don't have they unrelated. The two difference in the lot. There is no similarity in these two words. It shows that. And the cos theta is -1, then these two words are antonyms. These two words are opposite of each other. So these are some observation we can use for the analyzing the NLP data. And these are the mathematical view of cosine similarity of the two words to documents, to text, like that. And so we can use the Python coding for this. So we have some libraries, Python libraries for this. So we have a covector library for this cosine similarity. So we can say that cosine similarity of vector A to A, that means the self word, similarity between the self word, that should be 1. And the cosine similarity of word A to C, it's 0.7. So the cosine similarity ratio is 0.7. So we can directly calculate it by using some Python libraries. Yeah, after that, these are the basically mathematical view and mathematical views of my NLP, mathematics use of basically in a natural language processing. So that is the today's talk. So I'm happy to take questions. So if you have any question, you can please ask. Hello.
Uh, yes, so if there are no questions, then let's thank the speaker. Thank you, Kalyani. Thank you very much for that interesting talk. We'll move on to the next speaker. The next speaker is Anushka, and the title of her talk is Principle of Mathematical Induction. Anushka, you can take up to 3 o'clock and then introduce yourself and you can begin. Thank you, Kalyani.
Yes, thank you, ma'am.
Can you please stop sharing? Thank you. With mouse click. If you want to go back, you can use.
I can use that also, no?
Which
Keyboard like
yeah. And you can when you can write when it is on full screen mode. So
yeah, then make it full screen mode.
So now you can write. You can use the keyboard. Hello.
Hello. Hello.
No, she has to speak, no?
Hello. Good afternoon, everyone. I'm Anushka Roy, and I'm going to speak a few words on the topic Principle of Mathematical Inductions. So let's start. Principle of mathematical inductions is one of the most used tools in mathematics. Like it can be used in different fields. You can use it in number theory, game theory, calculus, combinatorics, and in any field of mathematics. Like if you appeared for Olympiad, then you'll obviously know that mathematical induction is often referred to as a savior tool because most of the people who appear for Olympiad, they almost take mathematical induction problems. They find it in the question paper to solve it. Mathematical induction can be defined as a mathematical proof method that is used to prove a given statement about any well-organized set. Like we have generally three steps in solving problems. Mathematical induction can be better understood if we take up problems. First, let me explain what the principle says, then I'll move on to the problems. The principle says that P of n be a statement involving any positive integer n. You can also say it as a natural number n. If P of 1 or any applicable base case is true, first we have to choose a base case. If the base case is true, then we have to go for the next one. Next, we have to consider a case, say for example, pk, where k is any integer, is any natural number, like you can select a random natural number. You have to consider it to be true. Then considering that one true, you have to go to proof for pk plus 1. K plus 1 is the integer which is just after k, like it's very general. And if it's true for p of k plus 1, then we say that p of n is true for all natural numbers n. It's a brief history of mathematical induction. It was in Plato's Parmenides, it was first given in a very naive way. Then Al-Fakri was written by Al-Karaji in 1000 AD. He applied mathematical induction in some fields, and then it slowly took pace, and now we use it. Okay, now let me move on to the general algorithm to solve the problems. Like at first, we need to go for some, I already said that we have a base case, so we have to first consider the base case. The base case, if the base case is satisfied, then we have to consider if P of k is true. For any natural number k, then we have to use that P of k to prove for P of k plus 1. Like now I've given a very simple example to make you understand that how this one is actually used. Like here you can see there are some cards placed one by one. I think you all can also see in TV advertisements that cards are placed one by one, and if one card is removed or one card is touched, then the whole thing automatically gets sorted. It's kind of that, here you take a base case, like you take a base card, then you work on it and make sure that your cards are at same distance. If the first card gets knocked, then the second card gets knocked, and the third card gets knocked, and so on. This is the general way to solve any induction-based problems. Now let me move on to the problems. I've written it. Like, okay, fine. I'm also writing it for you. Like, first, I've given a very simple problem, which we all know that sum of squares of natural numbers is n into a. Sorry. Yeah, we all know the formula of sum of squares of natural numbers n into n plus 1 into 2n plus 1 whole divided by 6. We can also prove it using the principle of mathematical induction. First, we have to prove it for P of 1. P of 1, we can see that 1 into 1 plus 1 into 2 into 1 plus 1, like it comes out to be 1 only ultimately. So we see that our base case is satisfied. Now we can go for P of k. Like we are assuming that P of k is true. This is the base case. The P of 1 is the base case here. Then we are considering that P of k is true. So, like the sum of natural squares of natural numbers till k square, like 1 square plus 2 square plus 3 square plus k square, is k into k plus 1 into 2k plus 1 by 6. That we are considering only. Then we have to prove it for P of k plus 1. We have to prove it that sum of squares of k plus 1 natural numbers is also satisfying our given formula. So that's what now we are doing. We already know this Sorry. Hello. Hello.
You're audible.
Okay. Sorry, we had some technical problems out here. I'm really sorry for that. So let's come back to our problem. So hello, am I audible?
Yes, yes, you're audible.
Okay, thank you. Okay, so let's come back to our problem.
What was it? Blue chair.
Hello. Sorry, I'm really sorry. We really had some great technical problems. Now it's sorted. So let's start with it. So we completed here that we assume that sum of squares of k natural numbers is k into k plus 1 into 2k plus 1 by 6. Now we have to use this one to go and prove p of k plus 1. Till this much we know the sum. It's this thing. For now we have to add this one and this one. Now doing it, we are getting this form k plus 1, k plus 2 into 2, k plus 3 by 6. Hence, we can see that p of k plus 1 is also true. Thus, p of n is true for all natural numbers n. Like here, you can take any natural number. It will obviously satisfy this thing because we have studied it earlier on in our school days. Now, this is the way to prove it. Now, let me go to some a bit tough problems. Yeah. 3 to the power, this is question number 2. 3 to the power n divides 3 to the power n many ones. First, let me make you understand the problem. 3 to the power n, where n belongs to any natural number, and 3 to the power n many 1 refers to 1, 1, 1. There, here we have 3 to the power n many ones. Now we have to prove that 3 to the power n divides 3 to the power n many ones. Here we have 3 to the power n ones. First, we need to prove for p of 1, that is the base case. We can see that 3 divides 1, 1, 1, hence the base case goes true. Now we have to consider that p of k is true. That is 3 to the power k divides 3 to the power k many ones. We have to consider this step. Now, using this step, we have to go for p of k plus 1. Like we have to prove that 3 to the power k plus 1 divides 3 to the power k many ones. Here, we have 3 to the power k plus 1 many ones. 3 to the power k plus 1 refers to 3 to the power k times 3. Now, we already know that 3 to the power k divides 3 to the power k many ones. 3 to the power k plus 1 many ones, we can write it in 3 blocks containing 3 to the power k many ones, like this one. This has 3 to the power k ones, this has 3 to the power k ones, and this again has 3 to the power k ones. Hence, in all total, we have 3 to the power k plus 1 many ones. Now we know that 3 to the power k divides this whole thing. Why? Because 3 to the power k divides this one, it divides this one, it divides this one. And in quotient we get something, then these many zeros, then something, then these many zeros and something. So we can say that 3 divides 3 to the power k many ones, 3 to the power k many ones divided by 3k. Like these individual blocks are also divisible by 3. So 3 divides these blocks divided by 3 to the power k. Hence 3 into 3 to the power k divides 3 to the power k plus 1 many ones. Hence we can prove 3 to the power k plus 1 divides 3 to the power k plus 1 many ones. Hence this completes this proof. Now I am moving on to the third problem. We are building an exponential tower that is root 2 power root 2 power root 2 power root 2. Here, and we are considering the base, like this is a sequence. So the base of the sequence, like we are considering A0 to be 1. We are considering it like A1, A2, A3, AN. This is a sequence of numbers where A0, we are starting it from 1. And A of n plus 1 is power root 2 to the power a of n, where n belongs to any natural number. We have to prove that this sequence is monotonically increasing. Monotonically increasing means a of n plus 1 should be greater than a of n for all n belonging to natural numbers. That is, if you take any n, you will find that a of n plus 1 is greater than a of n. That is every preceding term of the sequence will be less than the succeeding term of the sequence. And we have to prove that it is bounded by 2. It is bounded above by 2, that is, no term of the sequence will be greater than 2. We have to prove these two things. We already have that a of 0 is 1 and a of 1 is root 2 to the power of 1, because a of 1 is root 2 to the power of a of 0 and a of 0 is 1, so a of 1 is root 2. Now we are considering that now we have to prove that the sequence is monotonically increasing. That is, a of n plus 1 is greater than a of n. This is what we need to prove. And we can already see that p of 1 is true by this thing, because root 2 is greater than 1. Now we have to consider that p of k is true. That is, a of k is greater than a of k minus 1 for any k belonging to natural numbers. So now we have to prove that p of k. We have to prove p of k plus 1 using p of k. We have that a of k is greater than a of k minus 1, that we already proved here, that we already considered here. So root 2 to the power of a of k, we are raising this to root like to the power of root 2 to the power of a of k, like we are raising this thing to the power, is greater than root 2 to the power of k of a of k minus 1. This is possible because root 2 is positive. Similarly, hence we can say that a of k plus 1 is greater than a of k, because this term is a of k plus 1 term and this term is a of k. Hence, we are getting that a of k, p of k plus 1 is true. Now, hence p of n is monotonical. Hence, this sequence or p of n is monotonically increasing. This sequence is monotonically increasing. That we proved. Now we have to prove another thing, that it is bounded above by 2. We similarly, like using this method only, we can prove that a of k is less than 2 for any k which belongs to natural number. So root 2 to the power a of k is less than root 2 square. A of k is less than 2 we considered, so we are doing the same thing out here. That root 2 power a of k is less than root 2 square, which is equal to 2. Hence a of k plus 1 is less than 2. Thus, we also proved that a of n is bounded above by 2. Hence, we got that this series is monotonically increasing as well as it is bounded above by 2. Now let's go to a very interesting problem. Like many of us have gone through surprise tests in our school, but are surprise test really a surprise test? Like no, mathematically you can prove that no test is a surprise test, and using induction only you can prove that no test is a surprise test. So next time you are being asked that you will be getting to sit for a surprise test, you can say that no test can be a surprise test. So let's prove how I am concluding it. No test is surprise test. Like we have said that a test will be taken any day between Monday to Friday. Now say that on Friday the test cannot take place, right? Because the test is surprise test. So if the test didn't take place on Monday to Thursday, then we already know that it will take place on Friday. And if it takes place on Friday, then it's not a surprise to you, because as it didn't take place from Monday to Thursday, it will take place on Friday, hence it is no more a surprise to you. Thus Friday is getting discarded. Then similarly, we can prove that it will not take place on Thursday. Like Friday, we have already discarded from our list. Now we are considering between Monday and Thursday. Thursday, similarly, it cannot take place because it didn't take place from Monday to Wednesday. Similarly, by back induction, like following the same procedure, we can prove that this thing is that no test is a surprise test. Hence, next time, whenever you come through that you will be getting to sit for a surprise test, you can say that no test is a surprise test. Thank you. If you have any questions, please let me know.
Thank you, Anushka. If there are no more questions, I guess we can proceed. Shreyansh, how to expand this? Thank you, Neera.
Oh, so this one. Oh, the screen is being shared.
Oh, okay, fine. Mm. Okay, so the next speaker for today is Utsa. Utsa, are you there?
Yes, I'm here. Am
Yeah.
I audible?
Yes. So you are audible. So the title of Utsa's talk is Divisibility Rule of Odd Numbers. So you can take 20 minutes up to 3:35. 3:35 and then 5 minutes for discussion. Fine?
Okay.
Yeah.
Thank you. Is my screen visible? Okay, I think so. Good evening to everyone in this workshop. I am Utsha Dostidar. I am currently in foundational course of this BS degree. I am also pursuing physics honors in third year at Calcutta University. Mathematics was my general subject along my course. And while studying that, I followed my curiosity, uh, leading me to find this beautiful formula slash trick to find the divisibility rule for every odd number out there. So I'll help you find this divisibility rule for every odd number so that next time if you want to know if 1064 is divisible by 19 or not, you don't have to Google that. By the way, it is divisible. So here are a few divisibility rules, a few numbers that we know from our childhood, like the divisibility rule for 4. If the last 2 digits are divisible by 4, then the number is divisible by 4. For 5, it has to be the last digit has to be 0 or 5 for the number to be divisible by 5. For 9, it's similar to kind of 3. The sum of the digits has to be divisible by 9 for the number to be divisible by 9. And for 11, it's something interesting, like the difference of the sum of alternate digits has to be divisible by 11 for the number to be divisible by 11. Now, we never learned the divisibility rule of 19 because we probably never needed one. Back in our childhood, multiplication table till 13 could fetch us A plus grade. But just out of curiosity, what might be the divisibility rule for 19? Let's find out. For that, we might need few notations. Like I would present here this relation, as you can see. This relation here, as you can see, it is read as B is congruent to C mod M. What this basically means is M can divide the difference between B and C. In simple words, if B is divided by M, we get the remainder of C. It's the remainder. Now let's find out the divisibility rule for 19. So we may take any number, let's suppose n, and for n to be divisible by 19, we can say that n is congruent to 0 mod 19. Since if 19 divides n, the remainder will be 0. So also we can say n is equal to 10a plus b. I can represent any number as 10a plus b. For example, it's just simple expansion. For example, I'd show 74. We can write 74 as 7 into 10 plus 4. It's just like that. So I'd replace 10a plus b is congruent to 0 mod 19 for the number to be divisible by 19. But this doesn't necessarily mean that 10a will be divisible by 19. So we can say that there is a remainder z we find when we divide the number 10a by 19. So let me just multiply it by 2. I'll get 20a is congruent to 2z mod 19. I'd need this equation a bit later. You will see. Now, from these two equations, I can say if I subtract this equation from this equation, I'll get, let me write it again, 10a plus b. If I subtract it, I'll get b is congruent to minus z mod 19. Let me just again multiply it by 2. I'll get 2b is congruent to minus z mod 19. Now, coming to here, I'll need this equation too. I know if I multiply 19 into a, that will be a multiplication, that will be a multiple of 19 only. So it will always have the remainder 0 if it's divisible by 19. Then I can just subtract again and I'll get a is congruent to 2z mod 19, right? So I'll keep these two equations in hand. Now, if you just Google right now what is the divisibility rule for 19, you'll get that. Let's suppose we'll take 380 for example. From Google you can see, say, we have to take the last digit of the number and multiply it with 2. So this here will be 0 and add it to the rest of the number. So like 38 plus 0 equal to 38. Now we already know that 38 is divisible by 19, but I'll just do this simple process again. So 38, I'll do 8 into 2, it will be 16, add it to 3, I'll get 3 plus 16 equal to 19. So as you can see, 380 is divisible by 19. This comes from this formula only. If I add these two, equations, I'll get a plus 2b is congruent to 0 mod, sorry, it will be 2 since it's multiplied by 2. 0 mod 19. Here you see the 2b represents this part, the last digit of the number, and a represents the rest of the number. We get this number again and we can apply the same thing to this, get if the number is divisible by 19 or not. So now I found out that for 17, the formula was something like this. 3a plus 2b. For 15, it was 2b plus 5a. For 13, it was I guess we all can see the pattern here. The coefficient of b is actually the 10th position of the next higher 10 of this number. The next higher 10 is, for 17 is 20, right? We get 20. And the 10th position is 2. So we see that 2 to be the coefficient of b. And the difference of 17 and 20 is a coefficient for a. 3, 20, if we subtract 17 from 20, we get 3. So that will be the coefficient for a. Similarly, for 15, it's 2b and 5a. For 13 also, it's the same. For an example, I would show for 57, let's say. 57. It would be 6b, since the next higher 10 is 60 and the 10th position is 6. So I'll take it to be 6. And the difference from 57 to 60 is 3. So 3a. Now let's just take a number and check if it is divisible by 57 or not. So I'll take 285 to check if this is divisible by 57. I'll multiply 5, 6, I get 30 into 28 into 3 will give me 84. 84 plus 30 gives me 114. I'll do the same thing. 4 into 6 will be 24. 11 into 3 33 plus 24, 57. Therefore, yes, 285 is divisible by 57. So as you can see, you can use this trick to find the divisibility rule for any odd number out there, and you can apply it. So if you have a doubt, you can share it in the comment section. And so I conclude my talk here. I thank all the professors and IITM for providing me with such an opportunity. So yes, thank you.
Thank you, sir. Thank you for the wonderful talk. I guess there are no questions on chat as well. No. Okay. So then we can proceed to the last speaker of the day. We have Shenbagam with us. So she is going to talk on, the title of her talk is Heart of DS, AI and ML. So let's welcome Shenbagam. You can take 15 minutes.
What is the time? Because Kunal is waiting for his speech also. So should I tell him to? Where? He's here. You said last speaker, that's why he is like. What is the time, ma'am? It's time. Okay.
Do you want to write something?
Not later, I can. Right, if you want to write, you have to make this full screen and then use this to write. Only if it is in full screen, you can use this to write. Full screen, how to do it? You can use this to write. If you want to rub, you just click on this. All right, thank you. And get started. Yeah, you can introduce yourself and next slide. Huh? Next slide. Okay. Mouse click, mouse click. Yeah, or keyboard, right? Yeah. Okay. Good afternoon, everyone. My name is Shen Begum. Today, I'm going to share my learnings and my thoughts around the importance of mathematics, statistics. Of course, there is one more, key point that is also we are going to discuss. So first of all, this is an interesting topic. As we know, the entire world is around this, right? So for anything, what is happening, any event which is happening in the world is on three major things. So yes, there is always a mathematics which is getting applied. Of course, the next extension of mathematics, we call it as applied mathematics. So statistics. So mathematics, statistics, both of them are structurally uh, build to make sure that we get data or information. So mathematics, statistics, and data. So this is what we are going to discuss. This is the key aspect of whatever is running in and around us, like be it any telecast or any business function, or in our day-to-day life, or taking a flight, or sitting at home and watching a movie on Netflix. Yeah. So math and stats, this is everywhere around us. And it goes this takes mathematics and statistics takes the principal building block of every event that is happening around us. So moving on, um, the importance of maths and statistics. This is everyone knows what is maths and what is statistics. I don't want to discuss in detail, but many of the times whenever we go for any programming or any logical problems, we always find something which is very very difficult. It's because of the lack of practice or lack of fundamentals. Yeah. So here in this session, I would like to emphasize the importance of mathematics and statistics along with data to make sure that we are able to do the programming or any such building blocks in IT or in any business industry, to make sure that we are able to build resilient and sustainable solutions. So moving on, let's discuss the key the special items in the data science or machine learning. So we can take this as a special one. So anything that we build, or we make some coding or do testing, validation. So any kind of activity related to business solutions or any problem, we have the machine learning. So here the major pillars are statistics, probability, calculus, and linear algebra. So basically these are the building blocks, basically the pillars. And if you talk about data science, or if you talk about AR, ML, together we say, like, we do this for a kind of, building a solution to a problem. So there would be a problem statement, and we associate the problem statement with the pain points, understand it, and then, do the data analysis, acquire the data, and then, we also do the archiving or any kind of data process. So any process around data is all about mathematics and applied mathematics, the so-called statistics. Okay, so once, if we know the importance, or if we know the significance and the depth of statistics, probability, and calculus, of course linear algebra as well, we are kind of these are the key things, like we would be able to come up with a constructive programming, an effective programming, be it any code for that matter, like if you want to do something in Python or C++ or for any language for that matter, or JSON or YAML or whatever, it ranges from wide variety of solutions. Like today you would be doing some data orchestration, tomorrow you would be doing some DevOps solution, or there would be an infrastructure setup, or there would be an auto scaling. So for any kind of solutioning, or a simple ERP construction, or a CRM, like customer relationship management solutions, or marketing solutions, any campaigns or leads or whatever, the data is structurally built with mathematics and statistics, which plays a vital role in the in providing solutions, and particularly on any activities related to data science or AI or ML. Any questions till this, please? Please feel free to interrupt me. Oh, yeah. Moving on to the statistics. The extensive way of looking at the data in the larger amount, humongous data, how to solve it, or how to come up with the solutions, how to apply our thoughts to bring business benefits to any organization, be it an industry sector or a government sector, with all the complaints like security, and then protocols and all of that. It's very important that we collect the data, present the data, and then analyze it to interpret the data, right? So we want to deal huge amount of data in order to provide better business solutions, or for better business making decisions, right? So business decisions, the key decisions that is going to build our business, that is going to provide value add services to the business, bringing insights then and there, all these are playing a vital role. So that is where we do the prototyping, data mapping, data aggregation, orchestrate the data, and then make it bring it, or break it into parts, and then orchestrate, and then move it to the respective layers, or the mods, or the parts, to make sure that we are able to experiment the data, we are able to see the patterns around the data, analyze the data for any organization. So I don't have to explain about the sampling we do, or the census we make, or the primary or the secondary data, but please feel free to interrupt me if you have any questions. Moving on to an important aspect of statistics. Today, if you look at any activity, be it stock trading, or any kind of analysis, right? Data plays the data and the information plays a vital role. In order to do that, we need to do a condensation, or an aggregation, or a summarization to conclude it, right? Okay, and here we can do multiple activities. There are thousands of processes involved in it, and we are also using multiple frameworks, right? Every process is always a framework which will have different rules, where we have to use within this framework. This is what has to be constructed in various stages, number 1, 2, 3, and till the nth step. So we have a lot of steps to achieve each and every kind of sampling method, or evaluation method, or basically to provide a foolproof solution. So that's where the significance of data completely built or surrounded by the strong the strong construction of mathematics and statistics. So moving on to the interesting thing, yes, this generation, we are pretty much fortunate to have so many things which is happening around us, right? So it can be anything, right? Start from the day one, we do everything from home, right? We do everything in the world is with us. So we do everything within the seconds, in whatever way we want to take our life, right? So this is all importance of the data and the statistics, which is completely bounded or surrounded or structurally built using programming, right? So the programming can be in any way. You can do any kind of programming, but it has the basic, the fundamental or the principle as mathematics and statistics, which plays a vital role in every breath we take, everything we do it across, the industry, no matter it is a government organization or a private organization or in a hospital or insurance provider. It can be a payer or provider. So from A to Z, what is happening in the world, everything is governed, or everything is analyzed, or everything is very, very thoughtful. The world is very, very thoughtful and meaningful because of the data, and the data or the information that we are receiving or that we are getting it as an insight is because of the construct we have, the important, the vital figures that we have as mathematics and statistics. Yeah, so I don't have to explain, about the algorithms. There are multiple algorithms we typically use in any programming languages. Other than choosing the right data structure as well, like binary search algorithm or a breadth first or a depth first or a merge sort, quick sort, so many things. There are I could say thousands of algorithms which are running in the industry, which is helping us in getting the insights from the data, classifying the data, making the world or making our life better on a daily basis, which is also helping the organizations to grow and the entire universe for a better prospect. So yeah, next thing is about an interesting point, which is HITL, human in the loop. So basically, this is something like, till now we were talking about data. We were also talking about, the key things. So basically our Bible, which is the mathematics and statistics. So around this, who is ruling or who is governing, who is the controller here? So it's about the human, right? Our human brain is doing all of this. So in order to make us, do all of this, the intelligence or the machine learning needs to be properly associated or make it much more relevant. Yes, we are doing it through the HATL. So we do the gathering of data. We also prepare the data, do the data wrangling, and then analyze the data, train the model, right? Because any machine learning or artificial intelligence for that matter, gather the right data, train the models, validate the models, right? So how do you validate the models? Validating the models is very, very important, and that is a significant phase in every machine learning or any programming construct we do for AI and ML, be it a chatbot or any kind of intelligence system for that matter. The HATL plays a vital role till we test the model and also endorse it, right? Endorse it, accept it in the respective acceptance environment or a QA environment, and then move it to deployment, right? So all of these are having hundreds and hundreds of algorithms, and all these algorithms are written in any language, any programming language, or in any coding with the strong principle around mathematics or a rule or a statistics mechanisms. Yeah. So coming to the ML framework, right? So when we talk about the ML framework, right, anything, whatever we build, that needs a prototype or a protocol or a framework which we need to follow, right? In order to have a volatile as well as a sustainable solution, a resilient solution, we need to know how we have to manage the data, how to build resilient systems, make it performant, measure the output, whatever is provided or whatever is delivered by the systems are as solutions, and then continuously make improvements. So we call it as continuous service improvements, or we continuously make continuous automation. So in order to drive all of that, all of this entire framework or this processes are all built through mathematics and statistics, which plays a vital role in our day-to-day business activities, for any domain or industry for that matter. Any questions till this point? Thank you. So moving on to the quality, right? The quality of data, right? So why do we need quality of data? Because my inferring the data, right? What I'm going to get it as a result? How can I, infer the data? So in order to infer the data clearly and loudly, we would need the machine learning algorithms or the processes to be closely bounded with data quality factors, right? So data quality factors are clearly driven through business rules in every orchestration of data or any kind of solution that we build. In such cases, we are understanding the data sets, we are automating the data sets using different processes or algorithms, and then we are also trying to rationalize it till we get the till we achieve our business goals, right? End of the day, derive the business insights to shape the organization to for the organization growth. Yeah. So here, just wanted to quote an interesting point here, right? So I'm going to build a system for an organization, right? So how are we going to do it? This is just a sample. I would like to share it with you all. So any system, it starts from like, when an organization is growing, right? So it starts with typically like 20 years back and all, we were like, trying to build a system. Typically, it would be a ERP system, and then ERP. Once we know the importance of ERP, so basically, like for example, in a educational system, it would be a students management system, something like that, right? So once we know the importance of that system, then we are also like when it comes to an organization, we need to we need to know the products within the organization, and then we have to sell the products, and that's where we have the CRM. So it is like we have the ERP system in place, and then we are building the CRM on top of it to make sure that we are able to market the product and sell the product. And then from there, we need to, once the products are getting sold, we know we have a huge list of products or the sales transactions. So now how to analyze it? So in order to analyze it, we need to kind of we started to pool the data in a enterprise data warehouse. So there we have got the data warehousing concept, and then here everything, all of this, right? So it comes with various mathematics and statistics. And once we have the data warehousing systems, we thought we were able to do the data mining, data analytics, right? So like 10-15 years back and all, we were predominantly keen in data mining and then data analytics. So basically to bring insights from the business data. And then we also started to grow advancedly in various aspects of the moving ourselves into cloud era. And then within while we are expanding ourselves onto the cloud, we also have the DevOps process in place to containerize our workloads, and then streamline it for a huge organization where we have millions of batch process or a real time streaming. It's very important that the batch process or the data organization has to happen from n number of sources, that we are getting it from multiple systems, right, within the organization, or there would be some external systems. Those would be a FTP file or some other file. Basically it would be some other source systems, and from there we are orchestrating the data. So all of this, right, for for all of this, the construct or the building block or the key thing is the programming, right? So how do you do this programming? So you are building this programming, right? You do the coding in terms of applying the mathematical rules or the processes or the algorithms along with the extension of mathematics, the applied mathematics, basically the statistics principle, to check or infer the data. So basically in any solution, whatever is running or anything which is happening in this world now is all related to multiple events, and these events are orchestrated through clear algorithms, and these algorithms are relying only on mathematics and statistics. Yeah. So here if you see in this snapshot, whatever I'm trying to say, we have the source systems, we have the data capture area, and from there we need to transform the data. Why are we transforming this data? This data needs to be aligned with my business outcome or my business requirements. So I'm processing the data using multiple tools. It can be anything. It can be a data prep or a data flow, or in case of AWS, it would be multiple other AWS components, or in case of Azure, we have multiple components. So choose the right technology. Again, any technology for that matter. We have the mathematics and statistics, which is build closely or behind the screen, the mathematics and statistics rules or the formula or the formulae which is getting applied here, which makes the data to move it into the curated layer, and from there I can do the data analytics and the AIML, which can be where again we have n number of technologies which is built using programming, and from there the data, right, the output, right. So the output is moved, right. The output is converted, right. The expectations are converted, the requirements are converted into the I would say that consumption area. So what is this consumption area? So consumption area is for the end users, right. So the business community, so the business community will come and take the data. They can pick up the data from the consumption area, so that they would be able to get inference. It would be sometimes they have to customize the reports, or some would be already built reports where you will have a simple SSRS reports, or a visualization reports, or Power BI reports. So, or you can build users or the business community people, they themselves frame simple SQL queries and find out what is happening or what is running in the respective portfolio of a organization. So all of this will come under the data consumption area. And of course in all of this framework, we do a lot of DevOps activity in order to orchestrate the data from my early source systems till the end of the till I get the data in wherever model. For example, the data consumption area will have the machine learning models also. So it would be easy for the end user to get those models as well. So net if you look at the way the entire industry is operating, is on mathematics and statistics, structurally built through multiple technologies, which is kind of ruling the world now. Okay, so what next, right? So we are here. Everything is we can get everything in a second, right? I mean, at least we are able to manage stuffs. We are able to organize our thing. We know everything. So now what next? What we have as humans? What is our responsibility? How do we do this? Yes, this is we have a lot of augmentation, right? So a lot of pros and cons in in the way we interpret the data. So it's important that we have to be socially responsible. Before that, every organization definitely there are constructs in applying the security principles or compliance. So that comes under the business requirements. So they I would say DevSecOps, DevOps, or we can DevSecOps is also like embedded in every program, so that we are completely constructed, or we are pretty much we are able to build resilient solutions using the secure systems, right? So what next we have it. So as humans, right, as young minds, it's very important that we have to take this IT industry in a reliable and a positive and a constructive way, to make sure that we apply effective mathematics and scientific or statistical solutions, to make sure that we improvise the way we are working for the betterment of our world, in terms of reshaping our business, making sure that we are able to automate, or we are able to continuously automate things, and make sure that we are able to we are able to create programs to also eliminate the any kind of abuses or bugs or any harmful which interrupts the business or the human society. So this is where our role is also, we have that. So we have a vital role here as humans, as young minds. It's very important that we apply these effectively, right? So what does that effectively means here is building a resilient solutions, a sustainable solutions, a green solutions. It can be a green cloud or any green implementations, or in any kind of matter. You take it as a green field implementation or a brown field implementation or a blue field implementation. So we have the security, the compliance, as well as the processes are built strongly through the respective technologies, built with mathematics and this one, to make sure that we are able to nullify the gaps that we have in our world. So that is where we can continuously keep automating, continuously build innovations, continuously share the innovative solutions to this universe. So this is possible only if we are able to understand the the detailed or the deep knowledge in mathematics and statistics, where which we have sophisticated algorithms, which we have a lot of algorithms. These algorithms are also built on a day-to-day basis to make sure that we are here to reshape this world for the constructive IT, to make sure that we have a wonderful decades and decades things which are available with us in this universe. Thank you so much for the opportunity. Thank you, everyone. Actually, there's one more talk and professors are waiting that. Yeah, mic.
Thank you, Shinbagam ma'am. As someone in the audience said, you will pitch, you'll give awesome pitches to the companies. So thank you for that wonderful talk. We have one last speaker, Kunal Gupta. He'll be talking on computational methods and applications using primary real analysis. So Kunal, maybe 10 minutes,
Yes, ma'am.
because the professors are already waiting. Do you want to write?
Yes, ma'am.
You can write, and then this is for eraser. You can write, and then if you want to run, just click that. Screen share.
Good evening, everyone. I'm Kunal Gupta, a diploma student of this degree, and my topic is computation methods and applications using primary real analysis. So, first of all, initially, what is the fundamental theorem for the calculus? So, why do we need a calculus? What is the use of calculus and how we do it basically? So the theorem is that calculus is the concept of differentiation and integration linking together. So what is a calculus? Calculus is like when we play with the differentiation and integration simultaneously. It is the basic need of the calculus. So what is differentiation? So differentiation is a method of finding derivative. What is a derivative? Means like instantaneous rate of change in function is called a derivative. It can be a single variable, it can be a one variable. For example, like x square. So if we want to find its derivative, it is 2x. Or we can take as cos x. So its derivative is minus of sin x. Same goes with integration. So what is an integration? Integration is a method of adding or sum. Like for example, if we have this graph, something like this, okay, and we want to find its area in the small parts. So what we can do, we can integrate. Integrate means the sum. So First, we will take this shaded part, then this, and then this. So we will sum all the shaded parts. So that will be the area. And we will do it by the integration. So that is integration. So let's move forward to the first topic, Raleigh's theorem. So what is a Raleigh's theorem basically? Raleigh's theorem means like if we have a function, Raleigh's theorem, if we have a function f which is continuous on a comma b and it is differentiable also. So such that f of a is equal to f of b is the condition and for which c belongs to a comma b and differentiation f dash c equal to 0. It is Raleigh's theorem that let's take for example you have an equation like minus x squared plus 6x plus 6. So it is an equation and we want to find the point of tangent where it is 0. And it is given that f of 1 is equal to f of 5 equal to minus 1. So according the condition says that if a function is given, it is differentiable and continuous at a comma b, a domain, and is so if it is equal, then its first derivative should be 0. So for this equation, if we will take its first derivative, it will be minus 2x plus 6 equal to 0. So after putting c here, it will be minus 2c plus 6 equal to 0. So c will be 3 and it is in the domain 1 comma 5 which is a comma b. So this means it satisfies the Raleigh's theorem. And we can also try converse also like we have to prove that we have given the domain, we have given the answer, so we have to prove that it is a Rayleigh or not. For example, if we have a solution of a equation written as cot x equal to x in the domain 0 comma pi by 2, so we have to check that it satisfies Rayleigh or not. So how we can do? So first we just simplify it. Cos x by sin x minus x equal to 0. So it will be cos x minus x sin x equal to 0. So what we did in the Rayleigh is we differentiated the equation to check that it is Rayleigh or not. So we have to inverse it. So it means we have to integrate it to find the main equation that we want. So if we will integrate it, so after integration, we will separately integrate cos x dx minus integration of x sin x dx. So it will be integration of cos x is sin x minus of, here we will apply chain rule for integration, x cos x plus sin x plus c. C is a constant part, it will always be there to make it a link with the main equation. So we can ignore it and we can take it. So in this case, we will ignore c and we will simplify it. So we will get minus sin x plus x cos x minus plus sin x minus sin x. So we got x cos x as our main equation. So we have to check that it satisfies Rayleigh or not. So how we can check? We know that their domain is 0 comma pi by 2. So if we will put the range 0 and pi by 2 in that equation fx, we will get to know that f of 0 equal to f of pi by 2. And it is x cos x is continuous in the range. So it means that it satisfies the Rayleigh theorem. So it means that solution cot x equal to x exists in pi by 2. So this is the converse of Rayleigh theorem. So now we will move on to MVT, also known as mean value theorem. So what is the difference between MVT and Rayleigh? So basic differences in Rayleigh, we note that f of a is equal to f of b. So it makes our work very easy to calculate. Basically, calculation become very easy. In mean value theorem, we don't know that f of a is equal to f of b. So we have to do the long procedure for it. So if f of a is equal to f of b in Rayleigh, we know that f of c is equal to 0. But here they are not equal, so f of c will be equal to f of b minus f of a divided by b minus a. So this is Rowley and MDT both are same, but the difference is that f of a is not equal to f of b. This is the only difference. So basically, if we assume equation, let's say hx, which is equal to f of x minus f of b minus f of a divided by b minus a into x minus a minus f of a is the general equation. So if you will see the function f here, this f satisfies the Rowley, and h of x is continuous and differentiable on a comma b, the domain given, and h of a is equal to h of b, which is equal to 0. You can calculate it. So this means that h satisfies Rowley. So yeah, so I guess we can take one example for that to make it more understandable. So yeah, for example, if we have a function f of x which is equal to root of x in 0 comma 2, where c belongs to 0 comma 2, it means we have a is equal to 0 and b is equal to 2. So yeah, what we will do, we should apply MBT. So this means first f dash x, you have to calculate the differentiation, first derivative. So first derivative of root x is 1 by 2 root x. So after applying MBT, we will get that for c belong to 0 comma 2, we will get f dash c equal to f of 2 minus f of 0 divided by 2 minus 0. This implies which is equal to f dash c, and f dash c is 1 by 2 root x, which means 1 by 2 root c. So f of 2 root 2 minus 0, f of 2 means you will put 2 in the fx, which is root x. So root 2 minus 0 divided by 2 is equal to 1 by 2 root c. So 2 c to cancel, and then you will get c is equal to 1 by 2. And the thing is that c belongs to 0 comma 2 as given in the question, and we have the value c half. So it means it satisfies the condition. So it means we have done it correct, and we have our mean value theorem is also proved. So next we will move on to Taylor series. So basically, what is a Taylor series? Taylor series is the expansion of a function in infinite sum, terms that are expressed. Okay, so to make it more clear, it means that Taylor series is an expansion of a function uh, in an infinite sum of terms that are expressed in the terms of function of a derivative at a single point. To make it more clear, this equation is like general equation is like f of c plus x minus c f dash c single derivative plus x minus c whole square divided by 2 factorial f double dash c till so on. So according to definition, it is an infinite series, and it is expressed in a term of functions derivative. Like function derivative is function is fx. We are checking it for point c. So derivative, here we have first derivative. It means x minus c to the power 1 divided by 1 factorial. Here we have second derivative, so x minus c whole square divided by 2 factorial. Same goes with f of c. It means f of c, here we will have x minus c to the power 0 divided by 0 factorial. So power 0 means 1, 0 factorial means 1. So it will be 1 into fc. So we will write only fc. So that's the logic. So we will start with 0, then 1, then 2. So it is a general equation. And for example, if c is equal to 0, then this is called the Maclaurin series. It will be f of x is equal to f of 0 plus x into f dash 0 plus x square by 2 factorial f double dash 0. This is the simplest case of Taylor series, also known as Maclaurin series. So we can have a Taylor series in many different forms. For example, e power x, sin x, cos x, and so on. So yeah, so next is interpolation. Interpolation means it is a process of estimating the unknown values in the given values. It is bit tricky thing to understand, so I will make it clear. So interpolation means like it is a process of estimating the unknown values falling between the known values. For example, if we have the data given as x, for it means that for x0, it means f of x equal to y. It is like this. If we will put x as 0, then we will get y as 10. It means f of 0 is equal to 10. So, and if x is 0, then y is 10. So we have to find the value at 3. Like f of 3 is not available to us. So that is called the interpolation thing. Interpolation used to find the final answer. So let's take an example of it. Like if we know that question is given something like this, if y0 is 3, y1 is 12, y2 is 81, y3 is 2000, and y4 is 100. And we have to calculate delta 4 y0. So we will use the interpolation method to find the value of delta ki power 4 y0. So the general method is like n means the terms 0, 1, 2, 3, and 4. Here we have yn, here we have delta yn, here we have delta square yn. We need delta 4. So we should start with delta square, delta yn, and then delta 4. We need delta 4. So that's why we will. So what is the value of yn? We know that y0 is 3. So y0 is 3. Then we will go like 12, 81, 2000, and 100. So delta yn is 12 minus 3, y1 minus y0. It will be 9. We will write is at delta y0. So we will do it again. Y3 minus y2. Oh, sorry, y2 minus y1. It will be 69. Then it will be 1919, and it will be minus of 1900. So we got the values of delta yn. Now we can calculate delta square yn as we calculated yn by the same method, like 69 minus 9. It will be delta square y0. It will be 60. Then delta square y1. It will be 1850. Then delta square y2 by as minus 3819. Same goes for delta qyn. Y0 it will be 1790. Then minus of 5669. So as you can see that after when we started subtracting, we had many terms, and in last for delta 4yn, we only are left with single term. So means here we can stop. That's the final answer. So delta 4yn will be minus of 5669 minus 1790. It will be minus 7459. So this is the basic concept of interpolation. It is used to find the missing terms and the difference between the derivative of the sum. Like, so I guess yeah. So that's all from my side. Thank you to Academic Cell for giving me chance. Thank you, ma'am. Yeah. Thank you so much.
Thank you, Kunal. Are there any questions? Okay, fine. So, thank you all for participating and listening to all the wonderful talks in the workshop. We hope you all enjoyed it. Now, we are already late for the final, the concluding event of the 3-day fest. So we now have Professor Vignesh with us, Bharti ma'am, and all our instructors as well. So we'll welcome them and then give away the prizes to the winners of the Olympiad and the quiz. And we also have a small token of appreciation for the academic cell, maths and stat academic cell. So now we have Professor Vignesh.
So Bharti is on her way, so she'll
Yeah.
be here. So please sit down, everybody.
Sir,
So
a few words.
yeah. So first of all, congratulations to the team for organizing an event like this. This is definitely of interest to students, and anytime there are many such activities, it's going to really help the students to learn. So thank you, team, for organizing such an event and uh, encouraging people to participate. And congratulations to the learners who have actively been involved. They attended the sessions. I'm sure it was interactive and fun. I also hope you learned a lot. And I heard that more than 500 people participated in the Olympiad as well. So it was quite good participation. So glad that significant number of people got involved in this. So congratulations to everybody who was involved. We hope that more and more students get involved in such activities, and this really helps in learning various things, not just what is the required content for your courses. So very happy to see this, and also I hope you are enjoying the campus. So I don't know if many of you have come here before, or like this, for some of you this might be the first time. So I hope you are enjoying the campus. You can also see the campus around. It's a beautiful campus with a lot of greenery and nice flora and fauna. So please do enjoy your stay here. Okay, congrats to everybody who was involved.
Thank you, sir. So once again, just to recall what happened over these 3 days. On day one, we had the final round of Olympiad, for which almost 163 people were selected for the final round. After the first round, which had around 500 to 600 people giving the first round, and then 163 people were shortlisted for the second round. We had 98 people participating in it, and now we have the final five with us, the winners. So they'll be given a certificate and 1,000 rupees of Amazon cash voucher. So that is for the top five. But all those who qualified the first round, all those who qualified the first round will be given a certificate telling that they have qualified the first round of Olympiad. It's not a small thing at all, because the questions were at a good level that you really need to be good to even qualify that. So definitely that will be appreciated with a certificate. And then on the second day, we had an informal quiz that was conducted by the student core team. It was so much fun, I guess, for all the participants, and definitely to you people who conducted it. So we have two winners from the quiz, right? So we have two winners who will be given IITM merchandise, right? Like they have the goodies, IITM goodies, so that will be given to them. And day three, today we had a workshop of wonderful 10 talks from learners, and Professor Amritanshu gave the invited lecture. So I guess you all enjoyed those talks online as well as offline. Yes, Bharti ma'am. Okay, so let's get started with some of the certificates, and then Bharti ma'am will join us soon. So okay, so we will give away the certificates to those who gave talks in the workshop. We had 3 talks with offline people. So Shenbagam ma'am, yes, for the wonderful talk. Deepak. Deepak Pandey.
Yeah. Thank you, sir.
Thank you. I hope you enjoyed it.
Yeah, very much. Thanks.
Deepak is also a part of our maths and stat academic cell.
Okay.
And Anushka Roy, she is also a part of the maths and stat academic cell.
Thank you. Congrats.
Thank you, sir. And Kunal, who patiently waited for his turn and we know.
Okay.
So Kunal,
Congrats.
so thank you to all the speakers. I hope you will participate in the upcoming workshops as well. And now, okay. So for those who qualified the first round of Olympiad, we have Yuvraj here. So since he is here, he can collect the certificate directly, Yuvraj. And yes, the winners of the Olympiad, the reveal of the top 5. The 5th position goes to Sarvesh Rajashekharan. Sarvesh. Congratulations, Sarvesh. It is to be noted that he gave the exam offline. So, congrats, Sarvesh. And let me announce the other 4 winners as well. So, the 4th position goes to Harshavardhan Sudarshan. Roll number 22F 3002893, Harshavardhan Sudarshan. The 3rd position, Teerth Joshi, 21F 1004286. So Teerth is also doing a project with 2 of our instructors, Shubhashish and Shubhajit. The 2nd position goes to Sajal Pal, 21F 1004365. And the 1st position to Vikas Maheshwari. Vikas, you had emailed me yesterday asking about when the prizes will be announced. Definitely, it is worth it, I guess. You're getting the 1st position. So, Vikas Maheshwari, 21F 1001555. So, these are the 5 winners of the Olympiad. And then the quiz winners, yes. So, the quiz that happened in hybrid mode. Yes, with 2 or 3 participants offline and everyone else online. The winners are Shantana Prasad, Dhananjay Prasad. That's one. Shanta Prasad. Shanta Prasad and Jay Narayan. Okay. Shanta Prasad and Jay Narayan Suresh. So they are the winners of the quiz. So you here? Okay.
Congrats.
Thank you so much.
All right. So,
Prize will be given later.
Yeah. Not my name.
Yeah.
That is not my name.
Yeah.
we'll
We'll
you are
give you
correct.
prize.
Okay.
I think they just want something to be handed to you.
Sure.
It's okay. Yeah.
Okay. Fine.
You should have a few which are empty so that you can write later.
No, actually, they're just going to get t-shirts.
Oh,
And they told that they're not here, so we.
that's all.
Okay.
So congrats to all the participants and the winners and the organizers.
Shubhajit, we give away for the core committee?
I think she's stuck in that meeting. She said she'll come after that. I don't know if it's. Shit, that's going on, is it? That's okay. And we'll just do it here.
Okay. So now let's give away certificate of appreciation to the core committee, the Maths and Stats academic cell, the core committee. Definitely, they need to be appreciated for the work done over the past few days. And this cell is very young. It was the mentor is right here. So yeah, so the mentor is right here, and the mentees have definitely worked well with him, and so this is just a small token of appreciation for the work that you have done. So let me call the names of those who are present here. Okay, so Jay Bhatia, Nishkarsh Sharma, Megha? Megha Mitra?
Thank you, sir.
Shreyansh? Yeah, so Shreyansh is the designer of our website. He has done a wonderful job. Okay, so we are making the website public today. All credits to Shreyansh. And Nishkash also. And Nishkash, okay, yeah. Anushka? Anushka Roy?
Thank you.
Deepak Pandey?
Thank you, sir.
Harshit?
Congrats.
Chaitanya?
Thank you, sir. Congrats.
And Shivang? Okay, Shivang is not here. Okay. So Megha, would you please come and say a few words about your experience with this cell? That's it. Okay, fine. Hello. Again, greetings from the academic cell. Actually, we just skipped a little part. Very sorry about that. So, a few people who qualified the preliminary round of Olympiad were not present at the day of the final Olympiad, but they are present now. So, I think we should give them prizes, right? Yeah, because they did qualify and it wasn't very easy. So, I would like to call Shom Shubhrode. A round of applause, guys. Why are you silent?
Congrats. I don't know if we have certificates ready for you.
We do actually, we do for pictures, but we will definitely write your name afterwards. Okay.
It's all right.
Thank you. Thank you.
Wait, Shomshuba, the certificate has come. Nishkash, you can volunteer as a core committee member. That's your responsibility.
Thank you, sir. Yes, sir. You can later Photoshop it. So it's okay.
Next, we have Rishabh Kumar. Rishabh. Again, Nishkash, sacrifice your certificate.
I have put it. Congrats, sir. All the best. Thank you, sir. All the best.
We have Kunal Gupta here. Kunal on the stage.
Congrats.
We have Diksha here. Diksha. Applause, guys. And Bearden, thank you so much, all of you. I wish none of you has been missed. And thank you so much, sir, for your patience with us again.
Thank you all, and all the best with the next term as well.
Thank you so much, sir. So since I came to the campus, the coolest faculty I have known is Vignesh, sir. Can we have a round of applause? Thank you so much. Thank you so much.
So we kind of have a buffer time here right now, and whenever a buffer time comes, it's the responsibility of me to fill it up. So here I go again. Bharti ma'am is actually a little busy with a few work, so we are waiting for him, for her, sorry. And meanwhile, I'll just conduct the online. Nishka, Chef, please help me out with the online chat. How many participants are there? 43. All right, we have a fair amount of participants online, and as we promised that immediately after the event, we will definitely have a fun interaction with the core committee members and all of the cell people, the mentors. So here we go. And right now, the floor is open to audience as well as the online participants. If you have any query, any kind of doubt regarding the cell or regarding this program, anything, just the floor is open. You can ask to me or to the core members, and we will be definitely addressing it. Website URL. Yeah, the website will be inaugurated in a very short time, and the URL will be definitely circulated inside the member spaces, and as well as a mail will go to you. When we get certificate, Harshit, if you were an offline participant, you would have got the certificate here itself, but you will be getting the certificate, the soft copy of it immediately after this event. How to join the core team? So I think that is the question I got the most. And each and every term, just before the term starts, we roll out a form from the academic cell. For one form for membership, one form for applying to the core committee. So you have to apply through the form. An interview will be scheduled with the instructors. If you clear the interview, you're invited to the core committee. And that's a similar process for everyone. How can I get the detailed solutions of Olympiad? So our team, Shreyansh Mishra, they are working on the website, and the detailed solutions will be uploaded on the resources page of the website. We will be inaugurating the website shortly. You will be seeing it there. And again, the solution will be circulated inside the member spaces. Is Olympiad final result out for online participants? Yeah, the final result is already out, and we will be circulating the result through the mail and also in the member spaces, so you can refer to it. When will the membership form be enrolled? The membership form will be rolled out just before the starting of the January term. Around 15? Around 15. So the membership form will be rolled out around 15. Yeah, thanks to you again and again. Any more questions, guys? Any more questions regarding the cell, regarding the program? What is the next event of the society? Okay. I can ask my team members as well, but as far as I know, the immediate after event of this cell will be inaugurating our website. So stay with us. It will be live in 5 minutes. And also we are planning for a few weekly activities in the member spaces. If you are a part of the member spaces of the 5 member spaces, you already know about it, that we are planning for some weekly activities to solve questions and have regular quizzes.
क्योंकि इसमें एक वेरिएबल का फॉर्मूला जो हमारा एक वेरिएबल का है
Not very soon,
हाँ
probably 1 or 2 months. But yeah, some activities, some events will be very regular. Any more questions? Want to share your feedback or suggestions? You can definitely do it here right now on the chat. Any suggestions for us or any feedback? How was your experience regarding this event? Guys, you can definitely unmute yourself and speak up. How was your experience regarding this 3-day event? How many of you have attended offline? How many were online? Who were online? How was your experience? How much engaging you found it?
Akshat, you did online. Okay, how was your experience, Akshat? Anyone who wants to speak can just unmute yourself and speak up. This is a fun interaction. Shuyash is saying that he has attended online. Okay, I wish your experience was good. Next time, please try to go for offline. Okay, so many people I can see attended online. You can unmute yourself. You can speak up for the cell if you want to share your experience or any suggestion or any feedback. If you have any idea for an event or if you want to be a part, just you can freely unmute yourself and speak. Is there any Google group or something for maths and statistic academic cell? Yeah, there are five. The members, we have 850 plus members as of now, and they all are divided among five Google groups, or we call it member spaces. So those are named after five famous groups: Abelian, Silo, Grothendieck, Euler, and Galois. So these are the five member spaces. If you fill up the membership form next time, you will also be a part of that. Does one need to be in Chennai to be in the core committee to conduct events? No, it's not mandatory that you have to belong to Chennai. Like for us, a lot of the members doesn't belong to Chennai. But you have to be a very active participant and very dedicated towards organizing the event. And if there is an offline event, just try to be present at Chennai 2 or 3 days prior to the event. Can you or someone share group link here? There is no common group. I'm very sorry, Vishwajit. There is no common group. There are five member spaces. If you have filled the membership form, you would be part of those member spaces. And as of now, there is no common group. All of you are following our social medias, right? Shyamsh, can you circulate the social media links in the chat? Okay, I'm just waiting for the next queries. Again, if any one of you wants to share the feedback or suggestion, you can freely unmute yourself and do it. Okay, Shuyash is saying he is part of a Abelian group. Would you like to share your experience with us, Shuyash? When they will share the form? The form will be shared around 15th of Jan, just before the starting of our next term. Here are the social media links of our community. You can follow it for the updates and notifications. Will we get the certificates for today's talk today or tomorrow? Utshu, actually the certificates were distributed here in offline mode, but as you were an online speaker, you will be getting the certificate soft copy within today or tomorrow, like within this day, through your mail. Any more questions? Any experience? Any suggestion? Any confession? Anything?
Yeah, that's because we didn't know that they were coming. We absolutely we were recording, right? No, no. That we had a list of people who qualified round one who were going to come for round two.
Okay, so I think this is the interaction, right? We can wind it up. Thank you for being here with us. And we're just asking for a 5 to 10 minutes buffer time, and we will be right back. Stay with us, don't go anywhere. And we'll be right back again. And meanwhile, if you have any queries, just feel free to write it in the chat or let us know, unmute yourself and let us know. Thank you.
You will be getting. Yeah, that's because we haven't printed the certificate. We didn't know you were going to come offline. No. No, no, these were printed. We're going to come and give your second round to put it offline. Only then we know that we're going to come. Yeah, there was a form. There was a form.
I was not given any.
You will be given. T-shirt every size.
It's going to be dirty. Thank you very much. You are saying everything is confidential. It's confidential. Please wait. Why did you guys not keeping right? I've given both the rounds. What is the form that it outlines?
It went to only the debit card.
Well, the shape that makes
And the form.
I think I but you. So the online one is of no use. Okay, now what about the quiz?
The quiz we are giving today.
So the motion test was going to be delivered by the no, I'm asking why have you called me offline? The motion test was going to be in the house. First, to be facilitated, but we have to contact with the offline store. The contacted base and the stock is there. दस ओलंपियाड वाले नहीं है 10 ओलंपियाड वाले
Even though people felt they were going to come offline, look at the number of certificates. These many people told they are coming offline. So you are anyway going to get the certificate. The certificate is it's not like only if you come offline to get it.
Not studio setup, huh? I was asking if I could skip coming here, skip around 60 participants filled up on the He's from the court and I have been communicating with him. You cannot say I'm Yes, sir. I get it, but what is the point of explaining what is circuit which is not working? Think about it. Just string play. String. No, no. I know this goes and where was I? That's right. Oh, you're doing meeting. Shreyansh. So for Olympiad, check out but definitely they'll get What up? Yeah. No, no. I can hide him, sir. No, I can hide. We'll take some photo. Okay, definitely. No, done. Shreyansh also will join us. Come. Okay, man. That's fine. Yeah. What was that? Hi, man. Chance will be there.
अरे दीपक मैं भी निकल रहा हूँ आज एक फोटो लेना था।
घर जा रहे हैं?
हाँ मतलब कल सुबह जा रहा हूँ, पता नहीं और कब कब मिलेंगे नहीं।
तो मैम चलता।
तो
तो
शायद ही हम। हाँ
अच्छा अच्छा, तो आज ही निकलेगा?
नहीं, कल सुबह निकलूंगा 4 बजे।
तो अभी रुकना, अभी मेरे कैंपस में रुक जाना, अभी अभी क्यों किया?
हाँ हाँ, नहीं मैं निकलेंगे 7 बजे।
7 साढ़े 7 तक मिल जाएंगे।
7 साढ़े 7 तक।
We are not planning for this.
Also,
Preliminary is already been said.
there is something for detail.
Hello. Hello, is anyone there?
Yes, sir.
Yes, sir. Actually, I'm not sure. I'm a student. Is meeting being conducted or it's ended?
I think so. Indeed.
Okay. Okay then. Thank you.
Hello, is anyone here? Hello?